Right now, you are falling through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013, and most people still have no idea. We live inside the KBC Void, a cosmic desert where matter is 20% thinner than it should be. This emptiness is warping our measurements of reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations. We will journey through the discovery that shattered cosmology, explore why 90% of space is hollow, and reveal what it means to exist in the cosmic outskirts. If you are ready to see the universe differently, hit that like button and subscribe. And tell me in the comments, do you believe the universe is infinite or finite? Now settle in, relax, we begin. The KBC Void is named after 3 astronomers who mapped its boundaries: Ryan Keenan, Amy Barger, and Lennox Cowie. What they found defied every expectation. Our galaxy, the Milky Way, sits near the centre of this void, surrounded by a region where galaxies are scattered like distant islands in an endless ocean. The void stretches so far that light travelling at 300 million metres per second takes 1 billion years to cross from one edge to the other. This is not a black hole. Black holes are dense, crushing singularities where gravity devours everything. The KBC Void is the opposite, a desert of space-time where matter is sparse, where galaxies are few, where the pull of gravity is weak. It is 7 times larger than any other void ever measured, a sphere of emptiness so vast it challenges the very foundation of cosmology. The problem is simple and profound. According to the cosmological principle, the universe should look roughly the same no matter where you stand. Matter and energy should be spread evenly across the cosmos, like grains of sand on an infinite beach. But the KBC Void breaks this rule. The density of galaxies here is 20 to 46% lower than the cosmic average, depending on where you measure. This is not a small discrepancy. This is a gaping wound in the fabric of our models. For years, astronomers resisted the idea. The void was too big, too empty, too improbable. The standard model of cosmology, built on decades of observations and refined with exquisite precision, does not predict structures like this. Voids should exist, yes, but not on this scale, not with this depth. Yet the data kept arriving, survey after survey, telescope after telescope, all pointing to the same conclusion. We are surrounded by absence. And the void is not just an oddity, it is a clue. It may explain one of the deepest mysteries in modern physics, the Hubble Tension. When astronomers measure how fast the universe is expanding, they get different answers depending on how they look. Observations of the nearby universe suggest a faster expansion rate than measurements of the ancient cosmos predict. The difference is small, but statistically significant. It has persisted for years, resisting every attempt at resolution. The KBC Void offers an explanation. Inside a region of lower density, gravity pulls less strongly. Galaxies are drawn outward toward denser regions beyond the void's edge, creating the illusion of faster expansion. The effect is subtle but measurable, an 11% increase in the local expansion rate, just enough to reconcile the conflicting numbers. If the void is real, it means our measurements were never wrong. We were simply standing in the wrong place. This changes everything. It means the universe is not as uniform as we believed. It means local structure matters, that our cosmic address influences what we see. It means we have been building our models on the assumption of homogeneity, but living in a region where that assumption fails. The void forces us to ask uncomfortable questions. What else have we gotten wrong? What other hidden structures lurk in the dark? And if we are surrounded by emptiness, what does that mean for the future of our galaxy, our civilization, our search for others like us? To understand what a void is, you must first understand what the universe is made of. Not stars, not planets, not even galaxies. The universe is built from emptiness, with matter sprinkled across the dark like foam on the surface of an infinite ocean. Cosmic voids are the largest structures in existence. They are vast, spherical regions where galaxies are scattered thin, where the density of matter drops to 1/10 the cosmic average, sometimes less. A typical void stretches 300 million light-years across. The largest voids, like the KBC Void, reach 1 billion light-years or more. These are not pockets of nothingness. They are cathedrals of space, echoing chambers where expansion reigns and gravity barely whispers. If you could stand inside a void and look around, you would see almost nothing. Galaxies would appear as faint smudges on the horizon, separated by gulfs so wide that their light takes hundreds of millions of years to cross the distance. The nearest galaxy might be 50 million light-years away, a loneliness impossible to comprehend. The void would feel like an ocean of darkness, stretching endlessly in every direction, with only the rarest islands of light breaking the monotony. But voids are not empty. They contain matter, just far less than the walls and filaments that surround them. Imagine a cubic meter of space, roughly the size of a large box. On average, the universe contains about 1 hydrogen atom per cubic meter. Inside a void, that number drops to 1 atom per 5 cubic meters. This sounds trivial, but across billions of light years the difference becomes profound. Matter exists, but it is diluted, spread so thin that gravity struggles to pull it together. Deep within the voids, in regions far from any galaxy or gas, the emptiness becomes absolute. You could travel for millions of light years and encounter nothing but the occasional stray hydrogen atom drifting through the dark. Even dark matter, the invisible scaffold that holds galaxies together, thins to near absence. These are the loneliest places in the cosmos, regions where the universe is almost exactly as it was in the moments after the Big Bang, smooth, uniform, and profoundly quiet. Voids occupy 90% of the universe's volume, yet they contain only a tiny fraction of its matter. Most galaxies cluster in dense regions, pulled together by gravity into filaments and walls that form the skeleton of the cosmic web. Voids are the spaces between these structures, the negative space that defines the architecture of existence. Without voids, there would be no filaments. Without emptiness, there would be no structure. The cosmic web is a network of matter stretching across the observable universe. It consists of 4 components: voids, walls, filaments, and clusters. Voids are the hollow regions, vast bubbles of low density. Walls are thin sheets of galaxies that form the boundaries of voids, regions where the cosmic mean density returns to normal. Filaments are the threads that connect walls, narrow bridges of galaxies that stretch for tens of millions of light years. Clusters are dense knots where filaments intersect, gravitational wells packed with thousands of galaxies. This structure is not random. It is the result of forces that shape the universe from its earliest moments. Voids form because gravity pulls matter away from them. As the universe expands, regions of slightly higher density attract more matter, growing denser over time. Regions of lower density lose matter, becoming emptier as galaxies drift toward denser surroundings. Over billions of years, this process carves the universe into a foam, with voids expanding and matter concentrating along their edges. The boundaries of voids are sharp and well-defined. Inside a void, the density of matter might be 10% of the cosmic average. At the edge, the density rises quickly to 20%, then jumps to 100% in the walls just beyond. This sudden transition makes voids easy to identify in galaxy surveys. You can trace their edges by counting galaxies, watching the numbers drop as you move inward and rise as you approach the surrounding structures. Voids are not static. They expand faster than the universe as a whole, driven by the outward push of cosmic expansion and the inward pull of gravity from the walls beyond. Inside a void, the local expansion rate is higher than the cosmic average because there is less matter to slow the expansion down. This makes voids into laboratories for studying dark energy, the mysterious force accelerating the universe's growth. The shape and evolution of voids encode information about the fundamental parameters of the cosmos, the density of matter, the strength of dark energy, and the rate of expansion itself. The KBC Void is an extreme example of this architecture. It is 7 times larger than a typical void, deeper in its underdensity, and positioned in a place that makes it impossible to ignore. We are not observers looking at voids from the outside. We are inhabitants, living inside one of the largest hollow regions ever discovered, watching the universe through a lens shaped by absence. And that absence changes everything we see. You cannot see a void. Not directly. Voids do not emit light. They do not glow in infrared or radio waves. They are defined by what is missing, by the galaxies that should exist but do not. To find a void, astronomers must count the light, measure the distances, and map the silence between the stars. The process begins with a survey. Telescopes scan the sky, capturing the faint glow of distant galaxies. Each galaxy appears as a smudge of light, its spectrum revealing how fast it moves and how far away it sits. The motion of a galaxy stretches or compresses the wavelength of its light, a phenomenon called redshift. Light from a receding galaxy shifts toward the red end of the spectrum, its waves stretched by the expansion of space itself. By measuring redshift, astronomers calculate distance. A galaxy with a small redshift is nearby, its light travelling only a few 100 million years to reach us. A galaxy with a large redshift is distant, its light crossing billions of light years. Plot enough galaxies in 3 dimensions, distance and direction, and the structure of the universe emerges. Walls of light, threads of galaxies, and voids, vast regions where the count drops to nearly 0. The KBC Void was discovered using near-infrared light, wavelengths longer than human eyes can detect. Infrared pierces through the dust that obscures visible light, revealing galaxies hidden behind cosmic clouds. Keenan, Barger, and Cowie used this advantage to survey thousands of galaxies, measuring their positions and calculating the density of matter in every direction. What they found was a spherical underdensity, a hole in the galaxy distribution centered near the Milky Way. The void stretches roughly 500 million light-years in radius, measured from our position to where the galaxy density returns to the cosmic average. Inside this boundary, the number of galaxies drops by 20 to 46% depending on the distance from the center. This is not a subtle effect. This is a massive deficit, a region where billions of galaxies are simply missing. To confirm the void, astronomers used multiple techniques. They analyzed the motion of galaxies, tracking how they fall toward denser regions beyond the void's edge. Inside a void, galaxies experience a gravitational pull from outside, dragging them outward toward the surrounding walls and filaments. This outward motion creates a measurable pattern in redshift data, a signal that reveals the void's presence even when individual galaxies are sparse. They also studied supernovae, brilliant stellar explosions that serve as cosmic distance markers. Supernovae of a specific type, called type Ia, always shine with the same intrinsic brightness. By comparing how bright they appear to how bright they should be, astronomers calculate their distance with precision. Light from supernovae inside the KBC Void travels through regions of lower density, and its behavior matches predictions for a void of this size and depth. Another method involves gravitational lensing, the bending of light by mass. As light passes through a void, it encounters less matter and bends less sharply than it would through denser regions. By measuring how light from distant galaxies is distorted as it crosses the void, astronomers can map the distribution of matter, both visible and dark. The results confirm what galaxy counts suggest. We are surrounded by a region of significantly lower density. The void also appears in measurements of the cosmic microwave background, the faint glow of radiation left over from the Big Bang. As this ancient light crosses the void, it loses energy in a process called the integrated Sachs-Wolf effect. Photons climbing out of the void's gravitational well are redshifted, cooling slightly as they escape. This creates a cold spot in the microwave sky, a subtle signature that matches the void's location and size. Every measurement points to the same conclusion. The KBC Void is real, it is enormous, and it should not exist. According to the standard model of cosmology, voids form through gravitational collapse. Regions of slightly higher density attract more matter, growing denser over time. Regions of slightly lower density lose matter, becoming emptier as galaxies drift away. But this process has limits. The standard model predicts a maximum void size based on the age of the universe, the density of matter, and the rate of expansion. The KBC Void exceeds this limit by a factor of 7. Simulations of cosmic structure formation show that voids as large and deep as the KBC Void appear in less than 3% of universes consistent with the standard model. This is not just unlikely, this is a statistical crisis. Combined with other anomalies such as the Hubble Tension, the existence of the void contradicts the standard model at a confidence level exceeding 6 standard deviations. Add the Hubble Tension, and the combined discrepancy reaches 7 standard deviations. 7 standard deviations is not a hint, it is not a clue. It is proof that something is wrong. Mapping the dark revealed more than a hole in space. It revealed a hole in our understanding, a gap between what we observe and what our equations predict. The void is a mirror, reflecting back the flaws in the models we built to describe the cosmos. And now that we have seen it, we cannot unsee it. The void demands an answer. The numbers are precise, and they are damning. Inside the KBC void, the density of matter drops 20 to 46% below the cosmic mean. This is not a rounding error. This is not a margin of uncertainty. This is a measurable absence, a deficit of galaxies so large it cannot be explained by chance. To understand what this means, imagine dividing the universe into identical boxes, each a billion light-years on a side. In most of these boxes, you would find a certain number of galaxies, a predictable count based on the average density of matter across the cosmos. This average is the cosmic mean, the baseline against which all structure is measured. The KBC void is a box where the count falls short, not by a few percent, but by 20 to 46% depending on where you measure. The void is not uniform. Near its centre, where the Milky Way resides, the density deficit reaches its peak. Here, the number of galaxies is roughly half what it should be. Move outward, and the deficit decreases. At a distance of 300 million light-years, the density begins to climb back toward normal. By 500 million light-years, the galaxy count returns to the cosmic average, marking the void's edge. This gradient is crucial. It means the void is not a random fluctuation. It is a structured underdensity, a spherical region carved by gravity into the fabric of space. The shape is consistent with what models predict for a void formed by gravitational collapse, but the size and depth are not. Standard cosmology allows for voids, yes, but not on this scale. The deficit translates into missing mass. If you calculate the total amount of matter that should exist within 500 million light-years of the Milky Way, based on the cosmic average, and then compare it to what is actually observed, the difference is staggering. Billions of galaxies worth of matter are simply absent, pulled away by gravity toward denser regions beyond the void's boundaries. This missing matter creates a gravitational imbalance. Inside the void, the pull of gravity is weaker than it should be. Galaxies feel less attraction from their surroundings, and more from the dense walls and filaments beyond the void's edge. This asymmetry drives an outward flow, a drift of galaxies toward regions of higher density. The outward flow is measurable. Astronomers track the motion of galaxies by analysing their redshift, the stretching of light caused by their movement through space. In a perfectly uniform universe, galaxies would move outward due to cosmic expansion alone, their velocities increasing smoothly with distance. But inside the KBC void, galaxies move faster than expected, their velocities inflated by the gravitational pull from outside. This effect explains the Hubble tension. When astronomers measure the expansion rate of the universe using nearby galaxies, they calculate a value known as the Hubble constant. The current best measurement from local observations is 73 kilometers per second per million light-years. But when the same constant is calculated from observations of the early universe, using the cosmic microwave background, the value drops to 67 kilometers per second per million light-years. The discrepancy is 9%. This may sound small, but in cosmology, 9% is enormous. The Hubble constant is one of the most fundamental parameters of the universe, governing how fast space itself expands. A 9% mismatch means either our measurements are wrong, or our understanding of the universe is incomplete. The KBC void offers a solution. Inside a region of lower density, the local expansion rate appears faster because galaxies are being pulled outward by gravity from beyond the void's edge. This creates an illusion, a local measurement that does not represent the global average. Calculations show that a void as large and deep as the KBC void could inflate the local Hubble constant by 11%, just enough to reconcile the tension. But there is a problem. The standard model of cosmology, known as lambda cold dark matter, does not predict voids this large or this deep. Simulations of cosmic structure formation show that voids like the KBC void appear in less than 3% of universes consistent with the standard model. The probability is so low that the void's existence contradicts the model at a confidence level of 6 standard deviations. 6 standard deviations is not a debate. In particle physics, 5 standard deviations is the threshold for claiming a discovery. 6 is proof. The KBC Void, by its mere existence, falsifies the standard model of cosmology. When combined with the Hubble tension, the contradiction becomes even more severe. The standard model fails to explain both the void and the discrepancy in expansion rates. Together, these anomalies rule out the model at a confidence level exceeding 7 standard deviations. This is not a minor correction. This is a crisis that demands a new framework, a revised understanding of how gravity shapes structure on cosmic scales. Some researchers have proposed alternatives. One possibility is modified gravity, a theory that alters the strength of gravitational attraction at very low accelerations. Under this framework, gravity becomes stronger on large scales, allowing structures to grow faster and deeper voids to form. Models based on modified gravity can produce KBC-like voids and simultaneously explain the Hubble tension, offering a unified solution to both problems. But modified gravity is controversial. It challenges decades of established physics, replacing Einstein's equations with a new set of rules. Many astronomers remain skeptical, preferring to search for solutions within the standard model rather than abandon it entirely. Yet the data persists. The void is real, the tension is real, and 20% of the matter is missing. The deficit is not just a number, it is a clue, a fingerprint left by forces we do not fully understand. The void demands an explanation, and so far the standard model has none to offer. For nearly a century, astronomers have known the universe is expanding. Galaxies drift apart, their light stretching toward red as space itself grows between them. The rate of this expansion is measured by a single number called the Hubble constant. It tells us how fast the universe grows, how old it is, and how its fate will unfold. But in recent years, something went wrong. 2 different methods for measuring the Hubble constant began giving different answers. The discrepancy started small, a whisper of disagreement buried in the margins of error. Then it grew. As measurements improved and uncertainties shrank, the gap widened. By the early 2020s, the tension had become undeniable. The first method looks at the nearby universe. Astronomers measure distances to galaxies using bright stellar explosions called supernovae, objects whose intrinsic brightness is known with precision. By comparing how bright they appear to how bright they should be, the distance is calculated. Combine distance with redshift, the stretching of light caused by expansion, and you get the Hubble constant. This local measurement yields a value of roughly 73 kilometers per second per million light-years. The second method looks at the ancient universe. The cosmic microwave background is a faint glow of radiation left over from the Big Bang, a snapshot of the universe when it was just 380,000 years old. This light carries patterns, ripples in density that reveal the fundamental properties of the cosmos. From these patterns, cosmologists calculate what the Hubble constant should be today, based on how the universe evolved over 14 billion years. This method yields a value of roughly 67 kilometers per second per million light-years. The difference is 9%. 9% may not sound dramatic, but in cosmology it is catastrophic. The Hubble constant is one of the most carefully measured quantities in science. Both methods are precise, refined through decades of observation and calibration. The uncertainty in each measurement is small, less than 2%, yet the values refuse to agree. This is the Hubble tension. It is not a minor discrepancy. It is a 5.3 standard deviation disagreement, a statistical anomaly so large it suggests something fundamental is wrong with our understanding. In particle physics, discoveries are claimed at 5 standard deviations. The Hubble tension exceeds this threshold. Possible explanations fall into 2 categories. Either the measurements are flawed, contaminated by systematic errors that inflate the disagreement, or the universe is not what we thought it was. For years, astronomers searched for errors. They recalibrated distance measurements, checked for hidden biases, and refined their models of stellar evolution. The tension persisted. Then came the KBC Void. If we live inside a massive underdensity, a region where matter is 20 to 46% below the cosmic mean, then our local measurements are biased by our location. Galaxies inside a void experience a gravitational pull from denser regions beyond the void's edge. This outward pull inflates their velocities, making them appear to recede faster than they actually are. The effect is subtle but measurable. Inside a void, the local expansion rate appears higher than the global average because galaxies are being pulled outward by gravity from surrounding structures. Calculations show that a void as large and deep as the KBC Void could inflate the local Hubble constant by 11%, just enough to reconcile the tension between nearby and distant measurements. This is not speculation, it is a testable prediction. If the void is causing the Hubble tension, then other observable effects should appear. The motion of galaxies should show a systematic outward flow, a drift toward denser regions beyond the void's boundaries. Recent observations confirm this prediction. Galaxies within the KBC Void move outward faster than expected, their velocities matching the pattern predicted for a region of lower density. Another prediction involves bulk flow, the collective motion of galaxies on large scales. Inside a void, galaxies should move coherently outward, driven by the gravitational pull from beyond the void's edge. Measurements of bulk flow within 250 million light-years of the Milky Way match the predictions of models that include the KBC Void, offering independent confirmation that the void is real and influencing local dynamics. But there is a problem. The standard model of cosmology, lambda cold dark matter, does not predict voids as large or deep as the KBC Void. Simulations show that such structures form in less than 3% of universes, consistent with the standard model. The void alone contradicts the model at 6 standard deviations. Combined with the Hubble tension, the standard model fails at 7 standard deviations. 7 standard deviations is not a hint of new physics. It is proof that the model is incomplete. The universe is more structured, more organized, and more variable than the standard model allows. The void and the tension are not separate problems, they are symptoms of the same underlying issue. Gravity does not behave on large scales the way we thought it did. Some researchers have proposed modified gravity as a solution. In this framework, gravitational attraction becomes stronger at very low accelerations, the regime that governs structure formation on cosmic scales. Stronger gravity allows matter to clump more efficiently, creating deeper voids and denser filaments. Models based on modified gravity can produce KBC-like voids and simultaneously explain the Hubble tension, offering a unified solution to both anomalies. Others remain skeptical. Modified gravity challenges Einstein's equations, the foundation of modern cosmology. Many astronomers prefer to search for solutions within the standard model, hoping that better data or refined simulations will resolve the discrepancies, but the data keeps arriving and the tension persists. The Hubble tension is not just a problem for theorists, it changes how we interpret the universe. It affects estimates of the age of the cosmos, the distance to faraway galaxies, and the distribution of dark energy. If the local expansion rate is biased by the KBC Void, then measurements made from our position cannot be trusted to represent the global average. We are not objective observers. We are inhabitants of a cosmic anomaly, watching the universe expand at a rate that should not be possible. The void is not just empty space, it is a lens, distorting our view of reality, and the tension it creates demands an answer. The universe does not expand at the same rate everywhere. This is the uncomfortable truth hidden inside the KBC Void. Stand in a region of lower density, and space appears to stretch faster. Stand in a denser region, and expansion slows. The effect is real, measurable, and profound. Inside the KBC Void, galaxies move outward faster than cosmic expansion alone would predict. The reason is gravity. Matter beyond the void's edge pulls galaxies outward, dragging them toward denser regions like walls and filaments hundreds of millions of light-years away. This outward pull inflates the velocities of nearby galaxies, making them appear to recede faster than they actually are. The effect is not subtle. Calculations show that the KBC Void inflates the local expansion rate by roughly 11%. This matches almost exactly the discrepancy between local and distant measurements of the Hubble constant, the number that governs how fast the universe grows. If we live inside a massive underdensity, then our measurements of cosmic expansion are biased by our location. Imagine standing at the bottom of a valley surrounded by hills. Gravity pulls you downward, toward the valley floor, but it also pulls you outward, toward the hills beyond. Now invert the picture. A void is not a valley. It is the opposite, a hill in the gravitational potential, a region where matter is thin and gravity weak. Galaxies inside the void experience an outward pull from denser regions beyond its boundaries, causing them to drift away faster than cosmic expansion alone would drive them. This outward flow is not uniform. Near the centre of the void, where the Milky Way resides, the pull is weakest because the surrounding matter is distributed almost symmetrically in all directions. Move toward the void's edge, and the asymmetry grows. Galaxies on one side of the void feel a stronger pull from the dense structures beyond that edge, accelerating them outward. The result is a gradient in velocities. Galaxies near the void's centre move outward slowly, while galaxies near the edge move faster. This gradient distorts redshift measurements, the stretching of light caused by motion through space. When astronomers measure the redshift of a galaxy, they interpret it as a combination of cosmic expansion and the galaxy's peculiar velocity, its motion relative to the expanding background. Inside a void, peculiar velocities are inflated by the gravitational pull from outside, making the universe appear to expand faster than it does on average. The effect compounds over distance. A galaxy 50 million light-years away shows a small inflation in redshift. A galaxy 200 million light-years away shows a larger inflation. By 300 million light-years, the accumulated effect reaches 11%, just enough to reconcile the Hubble tension. This is not a coincidence. The void offers a natural explanation for why local measurements of the expansion rate exceed predictions from the early universe. But the explanation comes with a cost. If the void is responsible for the Hubble tension, then our measurements of cosmic expansion cannot be trusted to represent the global average. Every distance measurement, every calculation of the universe's age, every prediction of its ultimate fate, all of these depend on knowing the true rate of expansion. If our local measurements are biased, then the numbers we have used for decades are wrong. This has implications far beyond the Hubble tension. Astronomers use the expansion rate to calculate distances to faraway galaxies. These distances are then used to map the large-scale structure of the universe, to study the distribution of dark matter, and to constrain the properties of dark energy, the mysterious force accelerating cosmic growth. If the local expansion rate is inflated by the void, then all of these calculations are affected. The void also influences the motion of entire galaxy clusters. Recent measurements show that galaxies within 250 million light-years of the Milky Way move coherently outward, their collective motion forming a bulk flow directed away from the void's centre. This bulk flow matches the predictions of models that include the KBC Void, offering independent confirmation that the void is real and driving large-scale motion. But there is a deeper problem. The standard model of cosmology does not predict structures that cause such large variations in the local expansion rate. According to the standard model, the universe should be smooth and uniform on large scales, with only small fluctuations in density. The KBC Void violates this assumption. It is too large, too deep, and too effective at distorting local measurements. Simulations of cosmic structure formation show that voids as extreme as the KBC Void form in less than 3% of universes consistent with the standard model. This low probability suggests that either we are extraordinarily unlucky, living in a rare cosmic outlier, or the standard model is incomplete. Combined with the Hubble tension, the standard model fails at 7 standard deviations, a level of disagreement that rules out the model with near certainty. Some researchers have proposed that gravity itself behaves differently on large scales, allowing structures to grow faster and voids to become deeper than the standard model predicts. Under this framework, called modified gravity, the outward pull from dense regions becomes stronger, amplifying the effect of the void on local expansion measurements. Models based on modified gravity can produce KBC-like voids and simultaneously explain the Hubble tension, offering a unified solution to both anomalies. The void does not just change how fast the universe appears to expand, it changes what we think we know about the universe's history, structure, and fate. Expansion is not uniform, gravity is not weak, and we are not neutral observers standing outside the cosmic machinery. We are inside it, falling through a hole in space, watching the universe stretch at a rate that should not be possible. The universe is not scattered randomly. It is organized into a vast network called the cosmic web, a skeletal structure billions of light-years across. Matter clusters along threads called filaments, intersects at dense nodes called clusters, and spreads across thin walls that surround massive hollows. These hollows are voids, the empty chambers that dominate the cosmos. The cosmic web is the largest known structure in existence. It spans the entire observable universe, threading through 14 billion light-years of space with a regularity that defies intuition. Galaxies are not islands. They are beads strung along the web's filaments, organized into patterns that reveal the invisible hand of gravity shaping the cosmos over eons. At the smallest scale are individual galaxies, collections of stars bound by gravity into spirals, ellipses, and irregular clumps. Galaxies cluster into groups, small gatherings of tens to hundreds of galaxies held together by mutual attraction. Groups combine into clusters, massive structures containing thousands of galaxies packed into regions a few million light-years across. Clusters are nodes in the web, the bright intersections where filaments meet. They are the densest places in the universe outside of black holes and neutron stars. Inside a cluster, galaxies move at speeds of thousands of kilometers per second, their orbits shaped by the collective gravity of trillions of stars. The space between galaxies is not empty. It is filled with hot gas, visible only in X-rays, a plasma heated to millions of degrees by the energy of galactic collisions. Clusters connect to each other through filaments, narrow threads of galaxies stretching for tens or hundreds of millions of light-years. Filaments are the highways of the cosmic web, the bridges that link dense regions across vast distances. They are not solid. They are loose collections of galaxies spread thin along the path of least resistance carved by gravity over billions of years. Filaments intersect walls, thin sheets of galaxies that form the boundaries of voids. Walls are two-dimensional structures, surfaces where the density of galaxies rises sharply above the cosmic mean. They mark the transition from emptiness to substance, the edge where voids meet the rest of the universe. And then there are the voids themselves. Voids occupy 90% of the universe's volume but contain only a tiny fraction of its matter. They are the spaces between the filaments, the negative space that defines the web's structure. Without voids, there would be no web. Without emptiness, there would be no organization. The cosmic web formed through a process called gravitational collapse. In the early universe, matter was spread almost uniformly across space, with only tiny fluctuations in density. These fluctuations were imprinted in the first moments after the Big Bang, ancient sound waves that rippled through the hot plasma of the infant cosmos. As the universe expanded and cooled, gravity amplified these fluctuations. Regions of slightly higher density attracted more matter, growing denser over time. Regions of slightly lower density lost matter, their galaxies drifting away toward denser surroundings. Over billions of years, this process carved the universe into a foam, with matter concentrating along the edges of bubbles and voids expanding in between. The pattern is fractal. On small scales, galaxies cluster into groups. On larger scales, groups cluster into filaments. On the larger scales, filaments connect into walls that surround voids hundreds of millions of light-years across. The structure repeats at every level, a hierarchy of organization driven by the universal pull of gravity. The KBC Void is part of this web. It is one of the largest bubbles in the foam, a region where the density of galaxies drops far below the cosmic mean. Surrounding the void are walls and filaments that mark the transition back to normal density. Beyond these boundaries lie other voids, other filaments, other clusters, all part of the same vast network. The Milky Way sits near the center of the KBC Void, positioned in one of the emptiest regions of the cosmic web. To one side lies the Laniakea supercluster, a massive concentration of galaxies spanning 500 million light-years. To another side lies the Shapley concentration, an even denser structure pulling galaxies toward it, with the force of 10,000 trillion suns. These structures define the void's edges. Galaxies inside the KBC Void are pulled outward by the gravity of Laniakea, Shapley, and other dense regions beyond the void's boundaries. This outward pull creates the illusion of faster expansion, inflating the local Hubble constant and contributing to the Hubble tension. The cosmic web is not static. It evolves as the universe expands. Filaments grow longer and thinner as space stretches between galaxies. Voids expand faster than the universe as a whole, driven by the outward push of cosmic expansion and the inward pull of gravity from surrounding walls. Over billions of years, the web becomes more organized, more structured, with matter concentrating into ever denser nodes and voids growing ever emptier. The web encodes the history of the universe. Its structure reflects the initial conditions of the Big Bang, the distribution of matter and energy in the early cosmos. By mapping the web, astronomers can trace how gravity shaped the universe over 14 billion years, revealing the fundamental properties of matter, energy, and space-time itself. The KBC Void is a window into this history. It is a fossil, a relic of the processes that carved the universe into its current form, and it is a challenge, a structure too large and too deep to be explained by the standard model of cosmology. The void exists, the web surrounds it, and somewhere inside we watch the cosmos unfold, suspended in a network we're only beginning to understand. The universe is mostly empty. Not slightly empty, not mostly empty. Overwhelmingly, absurdly, profoundly empty. 90% of space is void, regions where galaxies are scarce and matter thins to almost nothing. This is not a minor detail. This is the dominant feature of the cosmos, the baseline against which all structure is measured. Imagine a cube of space 1 billion light-years on each side. Inside this cube, galaxies cluster along thin threads and sheets, forming filaments and walls that trace the outline of a massive bubble. The bubble is a void. The threads are the edges. Most of the volume is hollow. Now imagine repeating this cube across the entire observable universe. The pattern holds. Voids dominate. Matter clusters along their boundaries, leaving vast interiors nearly empty. This is the architecture of the cosmos. A foam of bubbles with galaxies concentrated at the edges and almost nothing in between. The numbers are staggering. In a typical void, the density of galaxies drops to 1/10 the cosmic average, sometimes less. This means that if you were to travel through a void, you might cross 50 million light-years before encountering a single galaxy. In the densest regions of the void's interior, the distance between galaxies stretches to 100 million light-years or more. Deep inside a void, the emptiness becomes absolute. Here, the universe resembles its state shortly after the Big Bang, smooth, uniform, and quiet. The density of ordinary matter drops to 1 atom per 5 cubic meters, compared to 1 atom per cubic meter in the cosmic average. Dark matter, the invisible scaffold that holds galaxies together, thins to near absence. This thinness is not an accident. It is the result of billions of years of gravitational collapse. In the early universe, matter was spread almost uniformly across space, with only tiny fluctuations in density. These fluctuations were seeded in the first moments after the Big Bang, imprinted as ancient sound waves that rippled through the hot plasma of the infant cosmos. As the universe expanded and cooled, gravity amplified these fluctuations. Regions of slightly higher density attracted more matter, growing denser over time. Regions of slightly lower density lost matter, their galaxies drifting away toward denser surroundings. This process carved the universe into a foam, with matter concentrating along the edges of bubbles and voids expanding in between. The mechanism is elegant in its simplicity. Gravity pulls matter toward regions of higher density. As matter flows away from underdense regions, those regions become even emptier, creating a feedback loop that amplifies the initial fluctuations. Over billions of years, small differences in density grow into the massive structures we observe today: clusters, filaments, walls, and voids. The result is a hierarchical structure. Small voids merge into larger voids. Filaments connect into walls. Walls surround the largest voids, forming boundaries hundreds of millions of light-years across. The pattern repeats at every scale, creating a fractal geometry that pervades the entire observable universe. Voids are not perfectly empty. They contain a small population of galaxies, typically dwarf galaxies that formed in the rare pockets of slightly higher density within the void. These void galaxies are different from galaxies in denser regions. They are smaller, less massive, and often isolated, separated from their nearest neighbours by tens of millions of light-years. The space between void galaxies is filled with diffuse gas, hydrogen and helium left over from the Big Bang. This gas is cold and neutral, barely interacting with light. It forms thin threads that connect galaxies, feeding them with the raw material for star formation. But the threads are fragile, easily disrupted by the motion of galaxies and the expansion of space. Voids grow over time. As the universe expands, the outward push of cosmic expansion combines with the inward pull of gravity from surrounding walls, causing voids to expand faster than the universe as a whole. This accelerated expansion increases the volume of voids, making them larger and emptier with each passing billion years. The largest voids stretch hundreds of millions of light years across, encompassing volumes so vast they strain comprehension. The KBC Void, at nearly 1 billion light years in diameter, is among the largest ever measured. But it is not alone. Surveys of the cosmic web have identified thousands of voids, each a hollow chamber carved by gravity into the fabric of space. The emptiness is not uniform. Near the centre of a void, the density reaches its minimum. Move outward, and the density begins to climb. At the edge, the density rises sharply, marking the transition to walls and filaments where galaxies cluster. This gradient is smooth and well-defined, a boundary carved by the relentless pull of gravity over cosmic timescales. Voids are the scaffolding of the universe. Without them, there would be no structure. Filaments exist because voids push matter outward. Clusters form where filaments intersect at void boundaries. Galaxies congregate along walls because gravity pulls them away from the emptiness within. The universe is not built from matter alone, it is built from absence, from the spaces between the light. 90% hollow. This is the cosmos we inhabit, a universe dominated by emptiness, organised by gravity into a delicate balance between substance and void. The KBC Void is simply the largest example of this pattern, a chamber so vast it challenges our models and forces us to reconsider what we thought we knew about the universe's structure. We are not floating in a sea of galaxies, we are suspended in a foam of emptiness, clinging to the edges of a bubble that should not exist. Gravity does not fill voids, it empties them. This is the paradox at the heart of cosmic structure formation. The same force that pulls galaxies together also carves the universe into hollow chambers, vast regions where matter is scarce and expansion dominates. In the early universe, matter was distributed almost uniformly across space. There were no galaxies, no clusters, no voids, only tiny fluctuations in density, imprinted in the first moments after the Big Bang, ripples in the fabric of space-time so small they would have been invisible to any observer. But these fluctuations were enough. Gravity amplified them, turning whispers into roars over billions of years. Regions of slightly higher density attracted more matter. As matter flowed inward, these regions grew denser still, their gravitational pull strengthening with each passing million years. Galaxies formed in these overdense regions, clustering together into groups, then clusters, then massive concentrations of thousands of galaxies bound by mutual attraction. But for every region that gained matter, another lost it. Regions of slightly lower density saw their matter drift away, pulled toward the denser surroundings. As matter left, these regions became emptier. As they became emptier, their gravitational pull weakened further, accelerating the outflow. This feedback loop carved the universe into a foam, with matter concentrating along the edges of bubbles and voids expanding in between. The process is relentless. Gravity pulls matter away from underdense regions toward overdense ones, creating a network of flows that reshape the cosmos over billions of years. Galaxies drift along these flows, following invisible currents carved by the distribution of matter across hundreds of millions of light years. Inside a void, the gravitational environment is unique. There is less matter, so the local gravitational pull is weaker. But beyond the void's boundaries lie walls and filaments, dense concentrations of galaxies that exert a powerful outward pull on anything inside the void. This asymmetry drives galaxies outward, away from the void's centre toward denser regions beyond its edge. The effect is measurable. Galaxies inside voids move with peculiar velocities, motions that deviate from the smooth expansion of the universe. These velocities are directed outward, away from the void's centre, creating a systematic flow pattern that reveals the void's gravitational influence. Studies of the KBC Void show exactly this pattern. Galaxies within 500 million light-years of the Milky Way move outward faster than cosmic expansion alone would predict, driven by the gravitational pull from structures beyond the void's boundaries. The outward flow inflates the apparent expansion rate. When astronomers measure the redshift of a galaxy, They interpret it as a combination of cosmic expansion and the galaxy's peculiar velocity. Inside a void, peculiar velocities are systematically inflated by the outward pull, making galaxies appear to recede faster than they actually are. This creates a local bias, a measurement that does not represent the global average expansion rate. Over time, voids grow. As matter continues to flow outward, the density inside drops further, and the void's boundaries expand. Simulations show that voids expand faster than the universe as a whole, driven by the combination of cosmic expansion and the gravitational pull from surrounding structures. This accelerated expansion increases the volume of voids, making them larger and emptier with each passing billion years. The largest voids, like the KBC Void, represent the extreme end of this process. They have been growing for billions of years, accumulating matter at their edges while their interiors become increasingly empty. The result is a massive underdensity, a region where the galaxy count drops 20 to 46% below the cosmic mean. But there is a limit. Voids cannot grow indefinitely. As they expand, their boundaries encounter other voids, forming walls where matter accumulates. These walls mark the transition from one void to another, regions where the outward flow from one void meets the outward flow from its neighbour. Galaxies collect along these walls, forming the filaments and sheets that define the cosmic web. Inside the voids themselves, a small population of galaxies remains. These void galaxies are different from galaxies in denser regions. They are smaller, less massive, and often isolated, separated from their nearest neighbours by tens of millions of light years. They form in the rare pockets of slightly higher density within the void, regions that manage to retain enough matter to collapse into galaxies despite the overall outward flow. Void galaxies evolve differently. They experience less gravitational interaction with neighbours, fewer mergers, and less tidal disruption. Their star formation proceeds more slowly, fueled by the diffuse gas that fills the void, rather than by violent collisions or gas stripping. The result is a population of galaxies that are bluer, less evolved, and more gas-rich than their counterparts in denser environments. The hierarchical nature of voids adds complexity. Large voids contain smaller subvoids, regions of even lower density nested within the larger structure. These subvoids have their own internal dynamics, their own populations of galaxies, and their own gravitational flows. The result is a fractal pattern, a hierarchy of emptiness that repeats at every scale. Approximately 1/3 of all galaxies reside in voids, scattered across the vast volumes that dominate the universe. Most of these are dwarf galaxies, small objects with masses below 1 billion times the mass of the Sun. They are the majority population of the cosmos, outnumbering massive galaxies by a factor of 10 or more, yet they receive far less attention because they are faint and difficult to study. Gravity does not just shape galaxies and clusters, it shapes emptiness, carving the universe into a network of hollows and concentrations that define the architecture of existence. The KBC Void is the largest example of this process, a chamber so vast it challenges the standard model of cosmology. And inside this chamber, gravity continues its work, pulling matter away, emptying the void further, reshaping the cosmos one galaxy at a time. Imagine living in a galaxy 50 million light-years from your nearest neighbour. No spirals shining in the night sky, no ellipticals glowing like distant lanterns, just darkness stretching endlessly in every direction, broken only by the faint smudge of light that takes tens of millions of years to cross the gulf between you and anything else. This is the reality for void galaxies. They are the cosmic hermits, scattered across the vast hollow chambers that dominate the universe. They are smaller than average, less massive, and profoundly isolated. Most are dwarf galaxies, objects with stellar masses below 1 billion times the mass of the Sun, faint and fragile, clinging to existence in the emptiest regions of space. Void galaxies are different. They are bluer than galaxies in denser regions, their light dominated by young, hot stars burning bright and fast. They have higher star formation rates, churning out new stars at rates that exceed what their mass would predict. They are gas-rich, their interiors filled with the raw material for star formation, hydrogen and helium that has not yet collapsed into stars. The reason is environment. Galaxies and voids experience less gravitational interaction with neighbours, fewer mergers, and less tidal disruption. In dense regions, galaxies collide, stripping gas from each other and triggering bursts of star formation. In voids, galaxies evolve in isolation, their star formation proceeding slowly and steadily, fueled by gas that accumulates over billions of years rather than stolen in violent encounters. This isolation shapes their properties. Void galaxies have younger stellar populations, stars that formed more recently than those in denser regions. They have lower metallicity, fewer heavy elements forged in the cores of massive stars and spread across space by supernovae. They are smaller in physical size, their stars concentrated in compact regions rather than spread across vast disks. But isolation is not absence. Void galaxies are not alone. They cluster into small groups and filaments, miniature versions of the cosmic web that spans the entire universe. These substructures form within the voids themselves, carved by the same gravitational processes that shape the larger web. The result is a hierarchy, voids within voids, with galaxies congregating along the boundaries of these nested structures. Approximately 1/3 of all galaxies reside in voids. This is not a small fraction. This is a significant portion of the galaxy population, objects that have been largely overlooked because they are faint, distant and difficult to study. Most void galaxies are dwarf systems, outnumbering massive galaxies by a factor of 10 or more. They are the majority population of the cosmos, yet they remain poorly understood. The evolution of void galaxies is slower. They assemble their stars over longer timescales, building mass gradually rather than in sudden bursts triggered by mergers. Their star formation histories are flatter, lacking the sharp peaks that characterize galaxies in denser environments. They grow in relative solitude, their development shaped by the slow accumulation of gas rather than violent interactions with neighbours. This slower evolution has consequences. Void galaxies at a given stellar mass have more massive dark matter halos than galaxies in denser regions. They reside in deeper gravitational wells, surrounded by more dark matter relative to their visible stellar content. This higher dark matter content influences their dynamics, their rotation speeds, and their susceptibility to external perturbations. Despite their isolation, void galaxies do experience mergers. Recent simulations show that void galaxies undergo mergers at rates comparable to galaxies in denser regions, but these mergers occur later, at lower redshifts when the universe is older. This delayed merger activity means void galaxies accumulate accreted stellar mass more recently than their counterparts in denser environments. The result is a population of galaxies with distinct assembly histories, shaped by the timing and frequency of their interactions. The Milky Way itself resides in a void, positioned near the centre of the KBC Void, one of the largest underdensities ever measured. This location is unusual. Most galaxies live in filaments and walls, regions where the density of neighbours is high and interactions are frequent. The Milky Way, by contrast, sits in a region where the galaxy count drops 20 to 46% below the cosmic mean. This raises a question. Is the Milky Way typical of void galaxies, or is it an outlier? Most void galaxies are small, blue and actively forming stars. The Milky Way is massive, contains a mix of young and old stars, and lies at the boundary between active star formation and quiescence. Its properties do not match the typical void galaxy profile. One explanation is that the Milky Way is not a true void galaxy. It resides near the centre of the KBC Void, but it is also part of the Local Group, a small cluster of galaxies that includes Andromeda and dozens of dwarf satellites. This local density is higher than the void average, creating a pocket of structure within the larger emptiness. The Milky Way may be isolated on large scales but clustered on small scales, a hybrid environment that shapes its evolution differently than galaxies in the deepest parts of voids. Another explanation is timing. The Milky Way has had billions of years to grow, accumulating mass through mergers with smaller galaxies and accreting gas from the surrounding intergalactic medium. Many of these interactions occurred early in its history, when the universe was denser and encounters were more frequent. The void environment may have influenced its recent evolution, slowing star formation and reducing interactions, but its current properties reflect a long history that predates the void's full development. Void galaxies are laboratories for studying galaxy formation in isolation. They evolve in environments with minimal external influence, their properties shaped primarily by internal processes rather than interactions with neighbours. By studying void galaxies, astronomers can disentangle the effects of environment from the intrinsic processes that govern star formation, gas dynamics, and stellar evolution. The KBC Void is the loneliest place we know. It is a chamber so vast that light takes 1 billion years to cross it, a region where matter is 20 to 46% thinner than it should be. Inside this chamber, galaxies drift in isolation, their light fading into darkness, their evolution proceeding at a pace dictated by absence rather than presence. And somewhere in this emptiness the Milky Way floats, a galaxy shaped by solitude, watching the universe expand at a rate that should not be possible. The universe has a cold spot. It appears in the oldest light we can see, the cosmic microwave background, a faint glow of radiation left over from the Big Bang. This cold spot is not random. It is a scar, a signature carved into the fabric of space by a massive void. The cosmic microwave background is a snapshot of the universe when it was just 380,000 years old. At that moment, the cosmos cooled enough for light to break free from matter, flooding space with photons that have been travelling ever since. This ancient light fills the sky, uniform to 1 part in 100,000, a near-perfect blackbody radiation at a temperature of 2.7 degrees above absolute zero. But the uniformity is not perfect. Tiny fluctuations appear, hot spots and cold spots that reveal the density of matter when the light was released. Hot spots correspond to regions of higher density. Cold spots correspond to regions of lower density. These fluctuations are the seeds of structure, the ancient ripples that grew into galaxies, clusters, and voids over 14 billion years. As light from the cosmic microwave background crosses the universe, it interacts with the structures it passes through. This interaction is called the integrated Sachs-Wolf effect, a subtle change in the energy of photons as they climb into and out of gravitational wells. When light enters a region of higher density, it gains energy, shifting toward the blue. When it leaves, it loses energy, shifting toward the red. In a static universe, these effects cancel perfectly. But the universe is not static. It expands, and in an expanding universe, gravitational wells change depth as light passes through them. If a well becomes shallower during the crossing, the photon loses more energy climbing out than it gained falling in. The result is a net redshift, a cooling of the light. This effect is strongest in voids, regions where the gravitational potential is shallow and expanding faster than the cosmic average. The KBC Void leaves a mark on the cosmic microwave background. As ancient light crosses the void, it loses energy in the integrated Sachs-Wolf effect, creating a cold spot in the microwave sky. The size and amplitude of this cold spot depend on the void's size, depth, and rate of expansion. For a void as large and deep as the KBC Void, the predicted cold spot is measurable, a temperature decrement of a few microkelvins spread across tens of degrees on the sky. Astronomers have searched for this signature. Observations of the cosmic microwave background reveal several cold spots, regions where the temperature is slightly lower than the surrounding average. The most famous is the CMB cold spot, a large anomaly in the southern sky that has puzzled cosmologists since its discovery. Some researchers have proposed that this cold spot is caused by a supervoid, a massive underdensity along the line of sight. The connection between voids and cold spots is testable. By measuring the distribution of galaxies and comparing it to the temperature fluctuations in the cosmic microwave background, astronomers can determine whether voids are responsible for the observed cold spots. Studies of the KBC Void show that its location and size are consistent with a measurable integrated Sachs-Wolf signal, confirming that the void influences the ancient light passing through it. But the effect is not limited to temperature. The void also influences the polarization of the cosmic microwave background, the orientation of the light's electric field. As light crosses a void, its polarization pattern is distorted by gravitational lensing, the bending of light by mass. This distortion creates a measurable signal, a subtle change in the polarization that reveals the void's presence, even when galaxies are too sparse to map the structure directly. The cosmic microwave background is a mirror. It reflects the structure of the universe at the moment light was released, but it also carries the imprint of everything the light encountered on its journey to us. Voids, filaments, clusters, all of these leave signatures in the temperature and polarization of the ancient glow. By analysing these signatures, astronomers can map the large-scale structure of the universe across billions of light years, tracing the cosmic web from its earliest moments to the present day. The KBC Void is visible in this map. It appears as a region of lower galaxy density, a cold spot in the microwave background, and a subtle distortion in the polarization pattern. All three signatures point to the same conclusion. We live inside a massive underdensity, a hole in space that has shaped the cosmos around us for billions of years. But the void does more than leave a mark on ancient light. It changes how we interpret the cosmic microwave background. The temperature fluctuations we observe are a combination of primordial fluctuations imprinted at the moment of recombination and the integrated Sachs-Wolf effect from structures along the line of sight. If we live inside a void, then our measurements of the primordial fluctuations are biased by the local structure, inflating or deflating the apparent amplitude of the fluctuations depending on the direction we look. This bias affects cosmological measurements. The cosmic microwave background is used to constrain the fundamental parameters of the universe: the density of matter, the density of dark energy, the rate of expansion, and the amplitude of primordial fluctuations. If our measurements are biased by the KBC Void, then the parameters we derive do not represent the global average. They represent the universe as seen from inside a massive underdensity, a special location that distorts our view of reality. Some researchers have proposed corrections. By modelling the integrated Sachs-Wolf effect from the KBC Void and subtracting it from the observed cosmic microwave background, astronomers can attempt to recover the true primordial signal. But this correction depends on knowing the void's exact size, depth, and rate of expansion, parameters that are still uncertain. The cold spot in the microwave sky is not just a curiosity. It is a window into the structure of the universe, a clue that reveals the presence of massive voids and their influence on the light we observe. The KBC Void is part of this story, a chamber so large it leaves a measurable imprint on the oldest light in the cosmos. And as we study this imprint, we are forced to confront an uncomfortable truth. The universe does not look the same from every location. We are not neutral observers. We are inhabitants of a cosmic anomaly, watching the universe through a lens shaped by absence. Is it coincidence that we evolved in a void? Or is there something about voids that favours the emergence of life? This question sits at the uncomfortable intersection of cosmology and philosophy, where data meets speculation and certainty dissolves into possibility. The Milky Way resides near the centre of the KBC Void, one of the largest underdensities ever measured. This placement is unusual. Most galaxies live in filaments and walls, regions where the density of neighbours is high and interactions are frequent. Only 1/3 of galaxies reside in voids, and most of these are small dwarf systems, not massive spirals like the Milky Way. The statistical probability of this placement is low, but not impossible. If galaxies are distributed randomly with respect to large-scale structure, then roughly 1/3 should reside in voids by simple geometric probability. But the Milky Way is not a typical galaxy. It is massive, metal-rich, and contains a central bulge surrounded by a thin disk of star-forming regions. Galaxies with these properties are more common in denser environments, not voids. One explanation is that the Milky Way is not truly isolated. It resides in the local group, a small cluster of galaxies that includes Andromeda, Triangulum, and dozens of dwarf satellites. This local density is higher than the void average, creating a pocket of structure within the larger emptiness. The Milky Way may be isolated on scales of hundreds of millions of light years, but clustered on scales of a few million light years, a hybrid environment that allows massive galaxies to form despite the overall underdensity. Another explanation is timing. The Milky Way has had billions of years to grow, accumulating mass through mergers with smaller galaxies and accreting gas from the surrounding intergalactic medium. Many of these interactions occurred early in its history, when the universe was denser and encounters were more frequent. The void environment may have influenced its recent evolution, slowing star formation and reducing interactions, but its current properties reflect a long history that predates the void's full development. But the deeper question remains: does living in a void increase the chances of developing intelligent life? Some researchers have speculated that voids might be safer environments, regions where the frequency of catastrophic events is lower. In dense clusters, galaxies collide more often, triggering bursts of star formation and flooding space with radiation from supernovae and active galactic nuclei. These events could sterilize planets, stripping atmospheres or bombarding surfaces with high-energy particles. In voids, by contrast, interactions are rare. Galaxies evolve in relative isolation, their star formation proceeding slowly and steadily. This gentler evolution might create more stable environments for planets, allowing life to develop over billions of years without the disruptive influence of nearby cosmic violence. If this hypothesis is correct, then voids might harbour a disproportionate fraction of habitable worlds, despite containing fewer galaxies overall. But there is a counter-argument. Voids are emptier, which means fewer stars, fewer planets, and fewer opportunities for life to emerge. The reduced density also means less heavy element production, fewer supernovae to seed space with the carbon, oxygen, and iron necessary for rocky planets and organic chemistry. Void galaxies are less metal-rich than galaxies in denser regions, their stars containing fewer of the elements essential for life as we know it. The KBC Void also raises questions about the Fermi paradox, the puzzle of why we have not detected signals from other intelligent civilizations. If the universe teems with life, where is everyone? One answer is that most civilizations evolve in denser regions, where galaxies cluster and the distance between stars is smaller. In voids, the vast distances between galaxies make communication and travel prohibitively difficult, isolating civilizations even if they exist. The scale of the void is staggering. The nearest large galaxy cluster outside the KBC Void lies roughly 500 million light-years away. A signal travelling at the speed of light would take 500 million years to cross this distance. Even if another civilization existed on the far side of the void and sent a message today, we would not receive it for 500 million years. By the time the message arrived, both civilizations might be long extinct. This isolation has profound implications. If intelligent life is rare, and if most of it evolves in denser regions, then we might be among the loneliest civilizations in the cosmos, separated from our neighbours by a gulf so vast it renders contact impossible. The void is not just an astronomical curiosity, it is a barrier, a cosmic moat that isolates us from the rest of the galaxy-rich universe. But isolation cuts both ways. If voids are safer, if they offer stable environments free from the disruptions of galactic collisions and radiation bursts, then they might be precisely the places where long-lived civilizations thrive. The emptiness that makes contact difficult might also create the conditions necessary for intelligence to develop and endure. The Milky Way's position near the centre of the KBC Void is either an extraordinary coincidence or a clue about the conditions necessary for life. If it is coincidence, then we are simply lucky, one of countless civilizations scattered across the universe, some in voids, some in clusters, with no particular bias. If it is not coincidence, if voids favour the development of intelligent observers, then we face a new problem: selection bias. Selection bias occurs when the act of observation influences what is observed. If observers are more likely to emerge in voids, then any intelligent civilization measuring the universe will find itself in a void, simply because that is where observers tend to be. This creates an illusion, a false impression that the universe is dominated by voids, when in fact most of the cosmos is dense. The anthropic principle suggests that we should not be surprised to find ourselves in a location compatible with our existence, even if that location is statistically unusual. The KBC Void forces us to confront this possibility. We cannot escape our vantage point. We cannot observe the universe from a neutral location. Every measurement we make is filtered through the lens of our environment, biased by the structure that surrounds us. If the void is real, then our understanding of the cosmos is shaped by absence, by the emptiness that defines our cosmic address. The luck question has no definitive answer. We do not know if voids favour life. We do not know if our location is coincidence or consequence. What we know is this: we evolved in a galaxy positioned near the centre of one of the largest voids ever measured, a region where matter is 20 to 46% thinner than it should be. And this placement, whether lucky or inevitable, changes how we see the universe and our place within it. The cosmological principle is the foundation of modern cosmology. It states that the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations on large enough scales. No place is special. No observer is privileged. This principle allows astronomers to extrapolate from what we see in our local region to the entire observable universe, building models that describe the cosmos as a whole. The KBC Void breaks this principle. We live inside a massive underdensity, a region where the galaxy count drops 20 to 46% below the cosmic mean. This is not a small fluctuation. This is a profound deviation from homogeneity, a structure so large it challenges the assumption that the universe looks the same from every vantage point. The void stretches roughly 1 billion light-years from its center to its edge, where the galaxy density returns to the cosmic average. The Milky Way sits near the center of this structure, a location that biases our measurements of the universe. Inside the void, the local expansion rate appears higher than the global average because galaxies are pulled outward by gravity from denser regions beyond the void's boundaries. This placement violates the spirit of the cosmological principle. If the universe were truly homogeneous, we should observe the cosmic mean density in our local region, not a deficit of 20 to 46%. The fact that we live in such an extreme underdensity suggests that either the principle fails on the scales we observe, or we are extraordinarily unlucky. The standard model of cosmology, lambda cold dark matter, assumes the cosmological principle holds on scales larger than a few 100 million light-years. Below this scale, structure is allowed. Galaxies cluster into groups, groups into clusters, clusters into filaments and walls. But above this scale, the universe should smooth out, with the average density converging to the cosmic mean. The KBC Void challenges this assumption. It spans scales of 1 billion light-years, larger than the scale at which homogeneity is supposed to emerge. Simulations of cosmic structure formation based on the standard model show that voids as large and deep as the KBC Void appear in less than 3% of universes. The probability is so low that the void's existence contradicts the standard model at 6 standard deviations. 6 standard deviations is not a hint of trouble, it is proof that something is wrong. Either the cosmological principle fails at the scales we observe, or the standard model needs revision. Both conclusions are uncomfortable. Both require abandoning assumptions that have guided cosmology for nearly a century. The implications extend beyond the void itself. If the universe is not homogeneous on scales of 1 billion light-years, then our measurements of cosmic parameters are biased by our location. The Hubble constant, the matter density, the amplitude of cosmic fluctuations, all of these depend on observations made from our position inside the void. If our position is special, then the values we measure do not represent the global average. This creates a crisis of interpretation. Astronomers use the cosmological principle to justify extrapolating from local measurements to the entire universe. If the principle fails, then this extrapolation is invalid. We cannot assume that what we see from inside the void reflects what an observer in a different location would see. Some researchers have proposed that the cosmological principle still holds, but on even larger scales than previously assumed. Perhaps the void is part of a larger structure, and homogeneity emerges only at scales of several billion light-years. But this proposal pushes the scale of homogeneity dangerously close to the size of the observable universe itself, making the principle difficult to test. Others have suggested that the standard model is incomplete, that gravity behaves differently on large scales than currently understood. Under modified gravity theories, structures can grow faster and deeper, allowing the KBC Void to form without violating cosmological constraints. These theories predict that voids like the KBC Void should be more common, reconciling the observation with a revised cosmological principle. But modified gravity is controversial. It requires abandoning Einstein's general relativity on cosmic scales, replacing it with new equations that alter the strength of gravitational attraction at low accelerations. Many astronomers remain skeptical, preferring to search for solutions within the standard model, rather than overturn a century of established physics. The KBC Void also raises questions about the cosmic microwave background, the ancient light left over from the Big Bang. This light is remarkably uniform, varying by only 1 part in 100,000 across the sky. The uniformity of the cosmic microwave background is often cited as evidence for the cosmological principle, proof that the early universe was homogeneous. But the void exists now, not in the early universe. It formed over billions of years through gravitational collapse, as matter flowed away from underdense regions toward denser surroundings. The fact that the early universe was homogeneous does not guarantee that the late universe remains so. Structure formation can amplify small fluctuations into large deviations from homogeneity, creating voids and clusters that violate the principle on scales smaller than the observable universe. The cosmological principle is not a law of physics. It is an assumption, a simplification that makes the mathematics of cosmology tractable. It has served astronomers well for nearly a century, allowing them to build models that explain the expansion of the universe, the cosmic microwave background, and the large-scale distribution of galaxies. But assumptions can be wrong. The KBC Void forces us to confront the possibility that the universe is not as uniform as we believed, that our location matters, and that the principles we use to build our models may not hold on all scales. We are not neutral observers standing outside the cosmic machinery. We are participants, embedded in a structure that shapes what we see and how we interpret it. The void is not just empty space. It is a challenge to the very foundations of cosmology, a structure that demands we reconsider what we thought we knew about the universe and our place within it. For decades, astronomers measured the universe with confidence. They calculated distances to galaxies, tracked the expansion rate, and mapped the distribution of matter across billions of light years. The numbers fit together, forming a coherent picture of a universe expanding smoothly from the Big Bang, its growth governed by the interplay of matter, energy, and gravity. Then the cracks appeared. Local measurements of the expansion rate exceeded predictions from the early universe by 9%. Surveys revealed massive structures that should not exist according to the standard model. The cosmological principle, the assumption that the universe looks the same from every location, began to falter under the weight of new data. The KBC Void explains why. We live inside a massive underdensity, a region where matter is 20 to 46% below the cosmic mean. This placement biases our measurements, inflating the apparent expansion rate and distorting our understanding of cosmic structure. What we thought we knew about the universe reflects not reality itself, but reality as seen from inside a hole. The Hubble constant is the most direct casualty. This number governs the rate at which the universe expands, determining how fast galaxies recede and how old the cosmos is. Local measurements using supernovae and other distance indicators yield a value of roughly 73 kilometers per second per million light-years. But calculations based on the cosmic microwave background, the ancient light from the Big Bang, predict a value of 67 kilometers per second per million light-years. This 9% discrepancy is known as the Hubble Tension. It has persisted for years, resisting every attempt at resolution. The KBC Void offers an explanation. Inside a region of a lower density, galaxies experience a gravitational pull from denser regions beyond the void's edge, inflating their velocities and making the universe appear to expand faster than it does on average. Calculations show that the void could inflate the local Hubble constant by 11%, just enough to reconcile the tension. But this solution comes with a cost. If the void is responsible for the Hubble tension, then the local measurements do not represent the global expansion rate. Every distance calculation, every estimate of the universe's age, every prediction of its ultimate fate, all of these depend on knowing the true rate of expansion. If our measurements are biased, then the numbers we have used for decades are wrong. The void also affects measurements of dark energy, the mysterious force accelerating the universe's growth. Dark energy is inferred from observations of distant supernovae, whose brightness reveals how fast the universe expanded at different times in its history. But if the void biases local measurements, then the inferred properties of dark energy may be incorrect. The standard model of cosmology, lambda cold dark matter, assumes that dark energy is a cosmological constant, a uniform force that fills all of space with the same density everywhere. But if we live inside a void, then our measurements of dark energy are influenced by the local structure, not just the global properties of the cosmos. This creates uncertainty about whether dark energy is truly constant or varies across space. The age of the universe is another casualty. The Hubble constant determines how long the universe has been expanding, and therefore how old it is. A higher Hubble constant implies a younger universe, because a faster expansion means less time has passed since the Big Bang. If the local Hubble constant is inflated by the void, then our estimate of the universe's age is too low. Current estimates place the age at roughly 13.8 billion years based on measurements of the cosmic microwave background. But if the void inflates the local Hubble constant by 11%, then the true age could be closer to 15 billion years. This difference matters. It affects calculations of when the first stars formed, when galaxies assembled, and when planetary systems like our own emerged. The void also distorts measurements of the matter density, the amount of ordinary and dark matter in the universe. Matter density is inferred from the large-scale distribution of galaxies, the motions of galaxy clusters, and the gravitational lensing of light by massive structures. But if we live inside an underdensity, then our measurements of matter distribution are biased by the local structure. The cosmic microwave background is affected as well. This ancient light carries information about the universe when it was just 380,000 years old, a snapshot of the early cosmos. The temperature fluctuations in this light reveal the density of matter at that time, the seeds of structure that grew into galaxies and voids. But as the light crosses the void, it loses energy in the integrated Sachs-Wolf effect, creating a cold spot in the microwave sky. This cold spot complicates interpretation. The temperature fluctuations we observe are a combination of primordial fluctuations from the early universe and the integrated Sachs-Wolf effect from structures along the line of sight. If we live inside a void, then our measurements of the primordial fluctuations are contaminated by the local structure. This affects estimates of the amplitude of initial density fluctuations, a fundamental parameter that governs how structure formed over cosmic time. The standard model predicts that voids as large and deep as the KBC Void appear in less than 3% of universes. This low probability suggests that either we are extraordinarily unlucky, or the standard model is incomplete. Combined with the Hubble tension, the standard model fails at 7 standard deviations, a level of disagreement that rules out the model with near certainty. What we got wrong is not just a number, it is a framework, an assumption that the universe is smooth and uniform on large scales, that our location is typical, and that our measurements represent the global average. The void shatters these assumptions. It reveals that the universe is more structured, more organized, and more variable than the standard model allows. Some researchers have proposed modified gravity as a solution. In this framework, gravitational attraction becomes stronger at very low accelerations, allowing structures to grow faster and deeper voids to form. Models based on modified gravity can produce KBC-like voids and simultaneously explain the Hubble tension, offering a unified explanation for both anomalies. Others remain skeptical. They argue that modified gravity requires abandoning Einstein's general relativity on cosmic scales, overturning a century of established physics. Many prefer to search for solutions within the standard model, hoping that better data or refined simulations will resolve the discrepancies. But the data persists, the void is real, the tension is real, and what we got wrong may not be a detail, but the foundation itself. The universe does not look the same from every location. Our measurements are biased by our cosmic address, and the numbers we trusted for decades may reflect not the global cosmos, but the local emptiness that surrounds us. The KBC Void is not alone. It exists within a hierarchy of cosmic underdensities, nested structures that reveal a universe more organized and more complex than the standard model predicts. Voids within voids, emptiness layered upon emptiness, all the way up to scales that approach the size of the observable universe itself. The term supervoid refers to voids that exceed typical sizes, structures larger than 300 million light-years across. The KBC Void, with a diameter approaching 1 billion light-years, qualifies as a supervoid, one of the largest known. But recent surveys suggest it may be part of an even larger structure, a super-void that encompasses multiple underdensities across billions of light-years. This hierarchy is fractal in nature. Small voids merge into larger voids, which themselves exist within even larger underdensities. The pattern repeats at every scale, from voids tens of millions of light-years across to structures that span a significant fraction of the observable universe. This fractal organization challenges the cosmological principle, the assumption that the universe smooths out on large scales. The local void is one example of this hierarchy. It sits adjacent to the KBC Void, a smaller underdensity roughly 150 million light-years across. The local void is closer to the Milky Way, positioned just tens of millions of light-years away, forming part of the local cosmic structure that includes our galaxy, the local group, and the Laniakea supercluster. Laniakea itself is embedded within the KBC Void. This supercluster, a massive concentration of galaxies spanning 500 million light-years, represents a local overdensity within the larger underdensity. The contrast is striking. Regions of higher than average density nested within regions of lower than average density, creating a complex tapestry of structure that defies simple categorization. Beyond the KBC Void lie other supervoids, each a massive chamber carved by gravity over billions of years. The Boötes void, discovered in 1981, was the first supervoid identified. It stretches 330 million light-years across and contains only 60 galaxies, far fewer than expected for a region of that size. The emptiness is so profound that early astronomers called it the Great Nothing. The Eridanus supervoid is another example. It lies in the southern sky, a massive underdensity associated with the cold spot in the cosmic microwave background. This void may extend up to 1 billion light-years across, comparable in size to the KBC Void. As ancient light from the Big Bang crosses the Eridanus supervoid, it loses energy in the integrated Sachs-Wolf effect, creating the observed cold spot. The CMB cold spot itself is controversial. Some researchers argue it is evidence of a supervoid along the line of sight, while others suggest it may be a primordial fluctuation, a rare statistical anomaly imprinted in the early universe. The debate remains unresolved, but the connection between voids and cold spots in the microwave background is now well established. The hierarchy extends upward. Some studies suggest that the KBC Void may itself be embedded within an even larger structure, a gigavoid spanning several billion light-years. This hypothesis is difficult to test because structures at these scales approach the size of the observable universe, making it challenging to distinguish local features from global properties. The existence of such large voids has profound implications. The standard model of cosmology predicts that the universe should become homogeneous, on scales larger than a few hundred million light-years. Structure formation proceeds through gravitational collapse, amplifying small fluctuations into galaxies, clusters, and voids. But this process has limits. The age of the universe constrains how much structure can grow, and the strength of gravity determines how deep voids can become. The KBC Void exceeds these limits. Simulations of cosmic structure formation based on the standard model show that voids as large and deep as the KBC Void appear in less than 3% of universes. The probability drops further for supervoids, structures that span multiple billions of light-years. The existence of such structures suggests that either we're extraordinarily unlucky, living in a rare cosmic outlier, or the standard model is incomplete. Some researchers have proposed that gravity behaves differently on large scales, allowing structures to grow faster and voids to become deeper than the standard model predicts. Under modified gravity theories, the strength of gravitational attraction increases at very low accelerations, the regime that governs structure formation on cosmic scales. This enhancement allows matter to clump more efficiently, creating deeper voids and denser filaments. Models based on modified gravity can produce KBC-like voids and simultaneously explain other anomalies, including the Hubble tension and the observed bulk flow of galaxies within 250 million light-years of the Milky Way. These models predict that voids should be more common and more extreme than the standard model allows, reconciling the observation of supervoids with a revised framework for cosmic structure formation. But modified gravity remains controversial. It requires abandoning Einstein's general relativity on cosmic scales, overturning a century of established physics. Many astronomers remain skeptical, preferring to search for solutions within the standard model rather than invoke new physics. The supervoid hierarchy also raises questions about the cosmological principle. If the universe contains structures that span billions of light-years, structures so large they approach the size of the observable universe itself, then the assumption of homogeneity may fail on all observable scales. This would mean that our measurements of cosmic parameters are fundamentally biased, reflecting not the global properties of the universe, but the local structure that surrounds us. The KBC Void is not an isolated anomaly. It is part of a larger pattern, a hierarchy of underdensities that reveals a universe more structured, more organised, and more variable than the standard model predicts. We are not floating in a uniform sea of galaxies. We are suspended within a nested set of voids, chambers within chambers, emptiness layered upon emptiness, all the way up to scales that challenge our understanding of the cosmos itself. You cannot photograph a void. Darkness does not emit light, and emptiness leaves no signature on a detector. To map a void, astronomers must trace its boundaries, counting the galaxies that surround it and measuring the silence in between. This is astronomy by absence, a discipline built on detecting what is not there. The techniques are indirect but powerful. The simplest method is galaxy surveys, systematic catalogues of millions of galaxies across vast regions of sky. Each galaxy's position is determined by its coordinates on the sky and its redshift, the stretching of light caused by the expansion of the universe. Combine these three coordinates, and the result is a three-dimensional map of the cosmos, revealing the distribution of matter across billions of light years. Galaxy surveys discovered the KBC Void. By plotting the positions of thousands of galaxies in the near-infrared, astronomers noticed a deficit in the galaxy count within 500 million light-years of the Milky Way. The deficit was not uniform. It was deepest near the centre and gradually increased toward the edges, forming a spherical underdensity that matched the expected profile of a void carved by gravitational collapse. But galaxy surveys have limitations. They detect only visible and infrared light, missing the diffuse gas and dark matter that fill the space between galaxies. To probe these invisible components, astronomers use gravitational lensing, the bending of light by a mass. As light from distant galaxies passes through a void, it encounters less matter and bends less sharply than it would through denser regions. This subtle effect is measurable. By analysing the shapes of thousands of distant galaxies, astronomers can reconstruct the distribution of matter along the line of sight, revealing voids, filaments, and clusters, even when individual galaxies are too faint to detect. Gravitational lensing studies of the KBC Void confirm what galaxy counts suggest. We are surrounded by a region of significantly lower density. Another technique involves the motion of galaxies. Inside a void, galaxies experience a gravitational pull from denser regions beyond the void's edge, creating a systematic outward flow. This flow is detected through peculiar velocities, the motion of galaxies relative to the smooth expansion of the universe. By measuring the redshift of galaxies and correcting for cosmic expansion, astronomers can calculate their peculiar velocities and trace the gravitational flows that shape their motion. Studies of peculiar velocities within the KBC Void show exactly the expected pattern. Galaxies move outward, away from the void's centre toward denser regions beyond its boundaries. This outward flow inflates the apparent expansion rate, contributing to the Hubble tension by making the universe appear to expand faster locally than it does on average. The cosmic microwave background offers another window into the void. This ancient light left over from the Big Bang carries information about the universe when it was just 380,000 years old. As the light crosses the void, it loses energy in the integrated Sachs-Wolf effect, creating a cold spot in the microwave sky. By measuring the temperature fluctuations in the cosmic microwave background and comparing them to the distribution of galaxies, astronomers can determine whether voids are responsible for the observed cold spots. The KBC Void leaves a measurable imprint on the cosmic microwave background. Its location and size are consistent with a cold spot several microkelvin below the surrounding average, spread across tens of degrees on the sky. This signal confirms that the void influences the ancient light passing through it, adding to the evidence that the void is real and not an artifact of incomplete data. Another method involves baryon acoustic oscillations, ancient sound waves that rippled through the early universe and left imprints in the distribution of galaxies. These oscillations create a characteristic scale in the clustering of galaxies, a standard ruler that can be used to measure distances and test cosmological models. By analysing the baryon acoustic oscillation signal in galaxy surveys, astronomers can determine whether the void distorts the expected pattern and whether models that include the void are consistent with observations. Recent tests of baryon acoustic oscillations within the KBC Void show mixed results. Some measurements are consistent with void models that explain the Hubble tension, while others favour the standard model of cosmology. The disagreement suggests that either the void is more complex than current models predict, or additional factors are influencing the measurements. Supernovae provide yet another probe. These stellar explosions shine with predictable brightness, allowing astronomers to calculate their distances with precision. By measuring the brightness and redshift of supernovae inside and outside the void, astronomers can test whether the void distorts distance measurements in the expected way. Studies show that supernovae within the KBC Void are consistent with void models, confirming that the local expansion rate is higher than the global average. The combined evidence from galaxy surveys, gravitational lensing, peculiar velocities, the cosmic microwave background, baryon acoustic oscillations, and supernovae all point to the same conclusion. The KBC Void is real. It is not an artifact. It is not a statistical fluke. It is a massive underdensity, a region where matter is 20 to 46% below the cosmic mean, spanning roughly 1 billion light-years from centre to edge. Seeing in the dark requires patience, precision, and creativity. Astronomers cannot point a telescope at a void and capture its image. They must build the picture piece by piece, layer by layer, using every available technique to trace the boundaries of emptiness and measure the subtle signals it leaves behind. The KBC Void emerged from this process, a structure revealed not by light, but by the absence of it, a hole in the cosmos carved by gravity and confirmed by decades of observation. The KBC Void is not completely empty. Embedded within its vast interior are pockets of structure, islands of light scattered across the darkness. The Milky Way itself resides in one such pocket, part of the Local Group, a small cluster of galaxies that includes Andromeda, Triangulum, and dozens of dwarf satellites. This local density is higher than the void average, creating a bubble of structure within the larger emptiness. The Local Group spans roughly 10 million light-years, a tiny fraction of the void's billion light-year diameter. It contains more than 80 galaxies, most of them dwarf systems with masses far below the Milky Way's. Andromeda is the largest, a spiral galaxy slightly more massive than our own, positioned 2.5 million light-years away. The two galaxies are falling toward each other, drawn by mutual gravity, and will collide in roughly 4 billion years. Beyond the Local Group lies the Local Void, a smaller underdensity positioned just tens of millions of light-years from the Milky Way. This void stretches roughly 150 million light-years across, forming part of the nested structure within the larger KBC Void. The Local Void is emptier than the KBC Void's average, containing fewer than 1/10 the expected number of galaxies for a region of its size. The boundary between the Local Group and the Local Void is sharp. Galaxies cluster in the Local Group, their density far above the cosmic mean. A few million light-years away, the density drops precipitously, marking the edge of the Local Void. This transition reveals the fractal nature of cosmic structure, with voids nested within voids and clusters surrounded by emptiness. Further out lies the Laniakea supercluster, a massive concentration of galaxies spanning 500 million light-years. Laniakea is not a single cluster, but a network of clusters and filaments, a region where the galaxy density exceeds the cosmic mean by a factor of 2 or more. The Milky Way sits on the outskirts of Laniakea, positioned near the edge where the supercluster transitions into the void. Laniakea is itself embedded within the KBC Void. This may seem paradoxical, a supercluster within a void, but it reflects the hierarchical nature of cosmic structure. The KBC Void is defined by its average density, which is 20 to 46% below the cosmic mean. Within this average, regions of higher and lower density exist, creating pockets of structure and subvoids that complicate the simple picture of emptiness. To one side of Laniakea lies the Shapley concentration, the largest gravitationally bound structure in the nearby universe. This massive overdensity contains tens of thousands of galaxies packed into a region roughly 100 million light-years across. The gravitational pull of the Shapley concentration is so strong it influences the motion of galaxies hundreds of millions of light-years away, including the Milky Way. The Shapley concentration sits beyond the edge of the KBC Void, positioned roughly 650 million light-years from the Milky Way. Its gravity pulls galaxies inside the void outward, creating the systematic flow that inflates the local Hubble constant and contributes to the Hubble tension. This outward pull is measurable, a bulk flow that reveals the gravitational influence of structures far beyond the void's boundaries. Between the Milky Way and the Shapley concentration lies the Great Attractor, a massive concentration of galaxies positioned roughly 200 million light-years away. The Great Attractor pulls the local group toward it at speeds exceeding 600 kilometers per second, a motion that has puzzled astronomers for decades. Recent surveys suggest the Great Attractor is not a single structure, but part of the larger flow pattern, driven by the Shapley concentration and other distant overdensities. The void's boundaries are not walls but gradients. As you move outward from the Milky Way, the galaxy density climbs gradually, passing through the local void, the edges of Laniakea, and finally reaching the cosmic mean at roughly 500 million light-years. Beyond this distance, the density continues to rise, transitioning into walls and filaments where galaxies cluster more densely than average. These walls form the boundaries between the KBC Void and neighbouring voids, regions where the outward flow from one void meets the outward flow from another. Galaxies accumulate along these boundaries, pulled by gravity from multiple directions and unable to escape the walls that trap them. The result is a network of filaments and sheets that define the cosmic web, the skeleton of the universe revealed by the distribution of matter. The Boötes void lies in a different direction, positioned roughly 700 million light-years from the Milky Way. This supervoid, discovered in 1981, was the first large underdensity identified, and remains one of the emptiest regions ever measured. It stretches 330 million light-years across, and contains only 60 galaxies, far fewer than expected for a region of that size. The Boötes void is not connected to the KBC void, but exists as a separate structure within the cosmic web. The Eridanus supervoid lies to the south, a massive underdensity associated with the cold spot in the cosmic microwave background. This void may stretch up to 1 billion light-years across, comparable in size to the KBC void. As ancient light from the Big Bang crosses the Eridanus supervoid, it loses energy in the integrated Sachs-Wolf effect, creating the observed cold spot. The distribution of these structures paints a picture of the universe as a foam, with voids occupying most of the volume and galaxies clustering along the edges. The Milky Way sits in one bubble of this foam, surrounded by the local group, bordered by the local void, embedded within the KBC void, and pulled by distant structures like Laniakea, Shapley, and the Great Attractor. This position is not central. It is not privileged. It is simply one location among countless others, each with its own local structure, its own neighbours in the abyss. But the KBC void is unusual. It is 7 times larger than a typical void, deeper in its underdensity, and positioned in a way that challenges the cosmological principle. The neighbours in the abyss, the local group, Laniakea, Shapley, are real, but they are pockets within a larger emptiness, islands of structure surrounded by a gulf so vast it distorts our measurements and forces us to reconsider what we thought we knew about the cosmos. The universe is accelerating. Dark energy, the mysterious force that drives cosmic expansion, is pushing space apart faster now than at any time in the past. This acceleration changes the fate of voids, transforming them from temporary structures into permanent features of the cosmos. Voids grow over time. As the universe expands, the outward push of dark energy combines with the gravitational pull from surrounding walls and filaments, causing voids to expand faster than the universe as a whole. This accelerated expansion increases the volume of voids, making them larger and emptier with each passing billion years. The KBC void is no exception. It has been growing for billions of years, accumulating matter at its edges while its interior becomes increasingly empty. The process is relentless. Galaxies drift outward, pulled by the gravity of denser regions beyond the void's boundaries. Over time, the void expands, its radius increasing as space itself stretches between galaxies. But dark energy changes the equation. In a universe dominated by matter, voids would eventually stop growing, their expansion balanced by the gravitational pull from surrounding structures. In a universe dominated by dark energy, this balance never arrives. The outward push of dark energy grows stronger as the universe expands, overwhelming the inward pull of gravity and driving voids to expand indefinitely. The consequences are profound. Galaxies inside voids will drift further apart, their separations increasing until neighbouring galaxies disappear beyond the cosmic horizon. the distance beyond which light can no longer reach us due to the expansion of space. In the KBC Void's deep interior, where galaxies are already separated by tens of millions of light years, this isolation will become absolute. Imagine a civilization evolving in the center of the void billions of years from now. Looking outward, they would see almost nothing. The nearest galaxies would lie beyond the cosmic horizon, their light stretched by expansion until it fades into darkness. The sky would be black, empty of all but the faintest glow from the cosmic microwave background. They would have no evidence that other galaxies exist, no way to know that the universe extends beyond their island of stars. This is the future of the KBC Void. As dark energy drives expansion, the void will grow emptier, its interior becoming a cosmic desert where galaxies vanish one by one into the accelerating darkness. The Milky Way, positioned near the void's center, will witness this transformation over tens of billions of years, watching as neighboring galaxies drift away and the cosmic web dissolves. But the Milky Way has a closer concern. Andromeda, the nearest large galaxy, is falling toward us, drawn by mutual gravity. In roughly 4 billion years, the two galaxies will collide, merging into a single, massive elliptical galaxy. This collision will occur long before the void's expansion isolates us from the rest of the universe. The merged galaxy, sometimes called Milkomeda, will be larger and more massive than either the Milky Way or Andromeda alone. It will contain roughly 1 trillion stars, the combined stellar populations of both galaxies, plus the stars formed during the collision itself. This new galaxy will sit near the center of the KBC Void, an island of light in an increasingly empty cosmos. As the void expands, Milkomeda will become more isolated. The local group, the small cluster of galaxies that includes the Milky Way and Andromeda, will merge into a single structure. But beyond the local group, other galaxies will drift away, pulled outward by the void's expansion and the gravitational attraction of distant structures. The Laniakea supercluster, the massive concentration of galaxies that includes the local group, will fragment over time. Galaxies on the outskirts of Laniakea will drift away, their motion driven by the expansion of space and the pull of structures beyond the supercluster's boundaries. Eventually, only the gravitationally bound core of Laniakea will remain, a collection of galaxy clusters held together by mutual attraction, while the rest disperses into the void. Beyond Laniakea, the Shapley concentration and other distant structures will continue to recede, their light redshifted by the expansion of space. Over tens of billions of years, these structures will cross the cosmic horizon, disappearing from view as the distance between them and Milkomeda exceeds the distance light can travel in the age of the universe. The void's expansion will also affect the cosmic microwave background. This ancient light, already faint at a temperature of 2.7 degrees above absolute zero, will continue to cool as the universe expands. Eventually it will fade into invisibility, its photons stretch to wavelengths too long to detect with any conceivable instrument. The future universe will be darker, emptier, and more isolated than the universe we observe today. Voids will dominate even more completely, occupying more than 90% of the volume and containing an ever smaller fraction of the total matter. Galaxies will cluster into gravitationally bound groups, islands of structure surrounded by vast oceans of emptiness. But this future is not certain. The nature of dark energy remains unknown. If dark energy is a cosmological constant, a uniform force that fills all of space with the same density everywhere, then the scenario described above will unfold. But if dark energy evolves over time, strengthening or weakening as the universe ages, then the future could be very different. Some models predict that dark energy will strengthen, accelerating the universe's expansion until it tears apart galaxies, stars, and eventually atoms themselves in a scenario called the Big Rip. Other models predict that dark energy will weaken, allowing gravity to slow the expansion and perhaps even reverse it, collapsing the universe back into a big crunch. The KBC Void offers a window into this uncertainty. Its existence suggests that dark energy may not be uniform, that local variations in density can create regions where expansion proceeds at different rates. If this is true, then the future of the void may differ from the future of the universe as a whole, creating pockets where expansion accelerates faster and regions where it slows. The void also raises questions about the ultimate fate of structure. If gravity behaves differently on large scales, as suggested by modified gravity theories, then the future evolution of voids may differ from standard predictions. Enhanced gravity could allow structures to remain bound over larger scales, preventing complete isolation and preserving connections between distant galaxy clusters. But these are speculations. What we know is this: the KBC Void is expanding, its interior becoming emptier, its galaxies drifting outward toward denser regions beyond its boundaries. This expansion will continue for as long as dark energy drives the universe's growth, reshaping the cosmic web and transforming the void from a temporary underdensity into a permanent feature of the cosmos. And somewhere in this void, the Milky Way floats, watching the universe expand at a rate that should not be possible, falling through a hole that grows larger with each passing moment. The KBC Void is not unique. It is part of a population, a collection of cosmic underdensities that pepper the universe like bubbles in foam. Some are small, spanning tens of millions of light years. Others are massive, reaching hundreds of millions of light years across. And a few, like the KBC Void, are supervoids, structures so large they challenge the standard model of cosmology. The Boötes void was the first supervoid discovered. Astronomer Robert Kirshner and his colleagues identified it in 1981, while surveying the distribution of galaxies in the constellation Boötes. What they found astonished the astronomical community: a spherical region roughly 330 million light-years across containing only 60 galaxies, far fewer than expected for a region of that size. The emptiness was so profound that early astronomers called it the Great Nothing. Here was a region of space where the galaxy count dropped to 1/10 the cosmic average, a void so deep and so large it defied existing theories of cosmic structure formation. The discovery forced astronomers to reconsider their models to account for structures that were not predicted by the equations governing gravitational collapse. Since then, thousands of voids have been catalogued. Galaxy surveys have mapped the cosmic web across billions of light years, revealing a universe dominated by emptiness. Voids occupy 90% of the volume, forming the hollow chambers around which galaxies cluster. Each void is unique, differing in size, shape, and depth, yet all share the same basic property. They are regions where matter is scarce and expansion dominates. The local void sits just tens of millions of light-years from the Milky Way, a smaller underdensity roughly 150 million light-years across. It is one of the closest voids, positioned adjacent to the local group and forming part of the nested structure within the larger KBC Void. The local void contains fewer than 1/10 the expected number of galaxies, its interior nearly as empty as the Boötes void despite being much closer. The Eridanus supervoid lies in the southern sky, a massive underdensity associated with the cold spot in the cosmic microwave background. This void may stretch up to 1 billion light-years across, comparable in size to the KBC Void. As ancient light from the Big Bang crosses the Eridanus supervoid, it loses energy in the integrated Sachs-Wolf effect, creating the observed cold spot, a temperature decrement of roughly 70 microkelvin spread across 10 degrees on the sky. The connection between the Eridanus supervoid and the cold spot remains debated. Some researchers argue the cold spot is evidence of a supervoid along the line of sight, while others suggest it may be a primordial fluctuation, a rare statistical anomaly imprinted in the early universe. Recent observations favour the void hypothesis, showing that the galaxy distribution along the line of sight matches the expected profile of a massive underdensity. The Sloan Great Wall is not a void, but its opposite, a massive concentration of galaxies stretching over 1 billion light-years across. It is one of the largest structures ever discovered, a wall of matter that forms the boundary between multiple voids. The Sloan Great Wall illustrates the duality of cosmic structure. Voids and walls are complementary, each defining the other through the gravitational processes that shape the universe. Galaxy surveys conducted over the past 2 decades have catalogued thousands of voids, each a hollow chamber carved by gravity into the fabric of space. The Sloan Digital Sky Survey, one of the largest astronomical projects ever undertaken, mapped the distribution of millions of galaxies across billions of light-years, revealing the full extent of the cosmic web. The data show that voids are not rare anomalies but common features, the dominant structures that define the architecture of the universe. But not all voids are created equal. Most are typical, spanning a few hundred million light-years and containing roughly 1/10 the cosmic average density. A few are extreme, reaching sizes and depth that should not exist according to the standard model. The KBC Void is among the most extreme, 7 times larger than a typical void and deeper in its underdensity. Recent studies have questioned whether even larger structures might exist. Some researchers have proposed that the KBC Void itself is embedded within a gigavoid, a super-supervoid spanning several billion light-years. This hypothesis is difficult to test because structures at these scales approach the size of the observable universe, making it challenging to distinguish local features from global properties. The possibility of nested voids, voids within voids extending to scales of billions of light-years, raises profound questions about the cosmological principle. If the universe contains structures that span a significant fraction of the observable universe, then the assumption of homogeneity may fail on all observable scales. This would mean that our measurements of cosmic parameters are fundamentally biased, reflecting not the global properties of the universe, but the local structure that surrounds us. Recent evidence from baryon acoustic oscillations supports the void hypothesis. Studies presented at the National Astronomy Meeting in 2025 showed that a void model is roughly 100 million times more likely than a void-free model when tested against 20 years of baryon acoustic oscillation data. This statistical confidence represents one of the strongest endorsements yet for the existence of the KBC Void and its role in explaining the Hubble Tension. But controversy remains. Some astronomers argue that the void is not as extreme as claimed, that improved measurements will show the underdensity as smaller or less deep than current estimates suggest. Others point to observations that appear inconsistent with void models, such as measurements of the cosmic microwave background that favour a homogeneous universe. The debate will continue until more data arrives. Future surveys, including those conducted by the Euclid Space Telescope and the Vera Rubin Observatory, will map the cosmic web with unprecedented precision, revealing the distribution of galaxies across billions of light-years and constraining the size and depth of voids. These observations will test whether the KBC Void is real, whether it is as large and deep as current estimates suggest, and whether it can explain the Hubble tension without invoking new physics. The universe is a universe of holes, 90% empty, dominated by voids that define the architecture of existence. The KBC Void is simply the largest example we have found, a chamber so vast it forces us to reconsider what we thought we knew about the cosmos. And as we map more of the universe, as we catalogue more voids and measure their properties with greater precision, we may discover that the holes outnumber the substance, that emptiness is not absence, but the foundation upon which all structure rests. Voids are laboratories for studying dark energy. This may sound paradoxical. How can emptiness reveal anything about a force that fills all of space? The answer lies in how voids grow, how they expand, and how their evolution depends on the properties of dark energy itself. Dark energy is the mysterious force accelerating the universe's expansion. It permeates all of space, exerting a negative pressure that pushes matter apart. Its effects are strongest in regions where matter is sparse, where gravitational attraction is weak, and where the expansion of space dominates over the clumping of galaxies. Voids are precisely such regions. Inside a void, the density of matter drops to 1/10, the cosmic average or less, weakening gravity's pull and allowing dark energy to dominate. As dark energy drives the expansion of the universe, it also drives the expansion of voids, inflating them faster than regions of normal density. The rate at which a void expands depends on the strength of dark energy. If dark energy is a cosmological constant, a uniform force with the same density everywhere and at all times, then voids expand at a predictable rate determined by the balance between dark energy's outward push and gravity's inward pull. But if dark energy evolves over time, strengthening or weakening as the universe ages, then the expansion rate of voids changes, leaving a measurable signature in their size and depth. Astronomers use voids to test these possibilities. By measuring the size distribution of voids at different distances, they can track how voids have grown over cosmic time. Voids observed at greater distances appear as they were billions of years ago, when the universe was younger and dark energy was less dominant. Comparing these ancient voids to nearby voids reveals how the properties of dark energy have changed over time. The technique is called void cosmology. It exploits the fact that voids are sensitive to the background cosmology, the fundamental parameters that govern the universe's expansion. The matter density, the dark energy density, and the overall expansion rate all influence how voids form, how they grow, and how their properties evolve. Voids also provide a clean environment for studying dark energy. Dense regions are complicated by baryonic processes, the physics of gas, stars, and galaxies that can obscure the underlying gravitational dynamics. Voids, by contrast, are avoided by matter and less contaminated by these processes. Their evolution is dominated by gravity and dark energy, making them ideal laboratories for testing cosmological models. The KBC Void offers a unique opportunity. Its extreme size and depth mean that dark energy has played a significant role in its evolution. If dark energy is stronger than expected, or if it varies across space, then the void's properties would differ from standard predictions. By measuring the void's expansion rate, its density profile, and its influence on nearby galaxies, astronomers can constrain the properties of dark energy with precision. Recent studies suggest that the KBC Void may be linked to the nature of dark energy itself. Some researchers have proposed that dark energy is not uniform, that it varies in strength across different regions of the universe. In this scenario, regions of lower matter density, like voids, would experience stronger dark energy effects, accelerating their expansion faster than regions of higher density. This variable dark energy hypothesis could explain why the KBC Void is so large and so deep. If dark energy is stronger inside the void, then its expansion would be accelerated beyond what the standard model predicts, creating a structure that exceeds the expected size limits. The void would grow faster, accumulate matter at its edges more efficiently, and create a deeper underdensity than gravitational collapse alone would allow. But variable dark energy is controversial. The standard model assumes that dark energy is a cosmological constant, uniform and unchanging across all of space and time. Introducing variations in dark energy requires abandoning this assumption, adding complexity to the model, and raising questions about what causes the variations. Another possibility is that dark energy is dynamical, that its strength changes over time but remains uniform across space. In this scenario, called quintessence, dark energy is not a constant, but a field that evolves as the universe expands. The properties of this field determine how dark energy influences the growth of voids, potentially allowing larger and deeper structures to form. Voids provide a way to test quintessence models. By measuring how the size distribution of voids has changed over cosmic time, astronomers can determine whether dark energy has strengthened or weakened. If quintessence is correct, then ancient voids should be smaller and shallower than nearby voids, reflecting the weaker influence of dark energy in the early universe. The KBC Void complicates this picture. Its existence suggests that either dark energy is stronger than expected, or gravity behaves differently on large scales, or both. Disentangling these possibilities requires precise measurements of the void's properties and careful comparison with cosmological simulations. Machine learning techniques have recently been applied to void cosmology, extracting information from void catalogues to constrain cosmological parameters. These algorithms analyze the distribution of void sizes, shapes, and depths, identifying patterns that encode the properties of dark energy and the overall expansion rate. Results show that void properties alone can constrain the matter density to within 10%, the amplitude of cosmic fluctuations to within 4%, and the spectral index of primordial fluctuations to within 3%. The KBC Void is part of this larger effort. Its extreme properties make it a test case for cosmological models, a structure that challenges the standard framework and forces astronomers to consider alternatives. If dark energy is variable, if gravity is modified, or if the universe is more structured than we believed, then the void offers a window into these possibilities. Voids also provide constraints on the equation of state of dark energy, the relationship between its pressure and density. This parameter determines how dark energy influences cosmic expansion, whether it accelerates at a constant rate or changes over time. Measurements of void properties, combined with other cosmological observations, can constrain the equation of state to within a few %, testing whether dark energy is a cosmological constant or something more exotic. The connection between voids and dark energy is profound. Emptiness is not absence, but a canvas on which the universe's fundamental forces paint their signatures. The KBC Void, with its extreme size and depth, is the largest canvas we have found, a structure that reveals the hidden influence of dark energy shaping the cosmos. And as we study this canvas, we are forced to reconsider what we thought we knew about the force that governs the universe's fate. Time is not absolute. It flows at different rates depending on where you are, how fast you move, and how strong the gravitational field around you happens to be. This is one of the foundational insights of general relativity, Einstein's theory of gravity and space-time. And inside a void, where matter is scarce and gravity weak, time flows differently than it does in denser regions. The effect is subtle but measurable. Space-time is curved by the presence of mass and energy, creating gravitational wells that slow the passage of time. Clocks placed deep in a gravitational well tick more slowly than clocks positioned far from mass, a phenomenon called gravitational time dilation. Inside a void, where the density of matter drops to 1/10, the cosmic average or less, the gravitational potential is shallower. This shallower potential means that time flows slightly faster inside voids than in denser regions. The difference is minuscule, measured in fractions of a second over billions of years, but it accumulates over cosmic timescales and affects how voids evolve. Galaxies inside voids experience a faster flow of time, their clocks ticking slightly ahead of clocks in denser environments. The implications extend beyond timekeeping. The rate at which time flows influences the rate at which physical processes unfold. Star formation, galaxy evolution, and the expansion of space itself all proceed at rates that depend on the local gravitational environment. Inside a void where time flows faster, these processes unfold more quickly than they would in a region of normal density. But the differences are small. The gravitational time dilation inside the KBC Void is negligible compared to the effects of cosmic expansion and the influence of dark energy. A civilization living inside the void would not notice anything unusual about the flow of time. Their clocks would tick at the same rate as clocks on Earth, their days would last 24 hours, and their years would span the same number of seconds. The more significant effect is the induced curvature of space-time on large scales. General relativity predicts that the distribution of matter shapes the geometry of space itself. In regions of high density, space curves more sharply, creating gravitational wells that trap light and slow time. In regions of low density, space flattens, approaching the geometry of an empty universe dominated by dark energy. The KBC Void induces hyperbolicity in space-time, a negative curvature that affects how light travels through the void and how distances are measured. This hyperbolic geometry creates subtle distortions in the apparent positions of galaxies, the brightness of supernova, and the redshift of light passing through the void. These distortions are small but measurable, offering another way to test whether the void exists and whether it influences observations. Dark matter complicates the picture. Inside voids, the density of dark matter drops along with the density of ordinary matter. The KBC Void is not completely empty. It contains galaxies, clusters, and dark matter, but all at lower than average density. This difference in mass distribution affects the gravitational potential, the flow of time, and the curvature of space-time within the void. Recent studies suggest that dark matter in voids behaves differently than dark matter in denser regions. Simulations show that dark matter halos inside voids are less concentrated, their density profiles shallower than halos in filaments and clusters. This reduced concentration affects the dynamics of galaxies inside voids, their rotation speeds, and their susceptibility to tidal disruption. The distribution of dark matter also influences the weak gravitational lensing signal from voids. As light from distant galaxies passes through a void, it is bent by the mass along the line of sight, creating subtle distortions in the shapes of background galaxies. By measuring these distortions, astronomers can map the distribution of dark matter inside voids, revealing how much mass is present and how it is organized. The KBC Void contains less dark matter than regions of normal density, but the exact amount remains uncertain. If the void's density contrast is 46%, as measured by galaxy counts, then the dark matter density should drop by a similar amount. This deficit of dark matter weakens the gravitational pull inside the void, allowing cosmic expansion to dominate and driving the outward flow of galaxies toward denser regions beyond the void's boundaries. The matter density inside the KBC Void is estimated at 8 to 14% of the critical density, compared to 31% in the universe as a whole. This difference means that the void contains roughly half the mass it should, a deficit of billions upon billions of solar masses spread across 1 billion light-years. This missing mass has been pulled away by gravity, accumulated at the void's edges, and concentrated into walls and filaments that surround the emptiness. The flow of time inside the void is also influenced by dark energy. This mysterious force dominates the expansion of the universe, exerting a negative pressure that pushes space apart. Inside voids, where matter is scarce and gravity weak, dark energy's influence is stronger, driving expansion faster and creating regions where space-time stretches more rapidly than in denser environments. This accelerated expansion affects the geometry of space-time, inducing a hyperbolic curvature that makes voids appear larger and emptier than they would in a static universe. The combination of reduced matter density, weaker gravity, and stronger dark energy creates an environment where time flows slightly faster, space expands more quickly, and the evolution of structure proceeds at a different pace than in the rest of the universe. But the differences remain small. The flow of time inside the KBC Void differs from the cosmic average by less than 1 part in a million, a discrepancy too small to detect with current technology. The curvature of space-time is similarly subtle, creating distortions in distance measurements and light paths that amount to a few percent at most. These effects are measurable in principle, but challenging to observe in practice. The KBC Void is not a time machine. It is not a region where causality breaks down or where the laws of physics behave strangely. It is simply a place where matter is sparse, gravity is weak, and the expansion of space dominates over the clumping of galaxies. Time moves differently here, but only by the smallest of margins, a whisper of relativity echoing across the emptiness. There is a boundary. It is not sharp like a wall, not marked by a line drawn across space. It is a gradient, a transition zone where the density of galaxies climbs from the void's emptiness toward the cosmic mean. This is the edge of the KBC Void, the region where our local underdensity meets the rest of the universe. The edge begins roughly 300 million light-years from the Milky Way. Here, the galaxy count starts to rise, climbing from 46% below the cosmic average toward normal density. Move outward another 200 million light-years, and the count reaches the cosmic mean, marking the transition from void to the surrounding walls and filaments. This 500 million light-year radius defines the void's outer boundary, the distance at which the underdensity disappears and the universe returns to its expected structure. But the transition is not abrupt. It is smooth, a gradual increase in galaxy density that spans tens of millions of light-years. The boundary is not uniform. In some directions, the void extends further, reaching 600 million light-years or more before the density returns to normal. In other directions, the edge lies closer, perhaps 400 million light-years away. This asymmetry reflects the influence of surrounding structures, massive concentrations of galaxies that pull the void's boundaries inward or push them outward. The Laniakea supercluster sits near the edge. This massive concentration of galaxies spans 500 million light-years, positioned at the transition zone between the void's interior and the denser regions beyond. Laniakea is not entirely inside the void, nor is it entirely outside. It straddles the boundary, a structure embedded in the gradient where underdensity gives way to overdensity. Beyond Laniakea lies the Shapley concentration, one of the largest gravitationally bound structures in the nearby universe. This massive overdensity sits roughly 650 million light-years from the Milky Way, just beyond the void's outer edge. Its gravity pulls galaxies inside the void outward, creating the systematic flow that inflates the local Hubble constant and contributes to the Hubble tension. The boundary region is dynamic. Galaxies drift outward from the void's interior, pulled by the gravity of structures beyond the edge. This outward flow creates a gradient in velocities, with galaxies near the edge moving faster than galaxies near the center. The flow is measurable, a bulk motion that reveals the gravitational influence of the surrounding cosmic web. The edge also marks a transition in the properties of galaxies. Inside the void, galaxies are smaller, bluer, and more actively forming stars. They evolve in isolation, their star formation proceeding slowly and steadily without the disruptive influence of frequent interactions. Near the edge, galaxy properties begin to change. Interactions become more frequent, mergers more common, and star formation rates more variable. The walls beyond the edge are the opposite of voids. They are thin sheets of galaxies where the density exceeds the cosmic mean by a factor of 2 or more. These walls form the boundaries between voids, regions where the outward flow from one void meets the outward flow from another. Galaxies accumulate along these walls, unable to escape the gravitational pull from multiple directions. Filaments connect the walls, narrow threads of galaxies stretching for tens or hundreds of millions of light years. These filaments are the highways of the cosmic web, the bridges that link dense regions across vast distances. They mark the transition from the void's emptiness to the structured regions where matter clusters into groups, clusters, and superclusters. The KBC Void's edge is not static. It evolves as the universe expands, its radius increasing as space itself stretches between galaxies. Dark energy drives this expansion, pushing the boundary outward and inflating the void faster than regions of normal density. Over billions of years, the edge will move further from the Milky Way, expanding the void and increasing its volume. But gravity also shapes the edge. The surrounding walls and filaments pull inward, resisting the outward push of dark energy and slowing the void's expansion. The result is a balance, a dynamic equilibrium where the edge expands but not as fast as it would in the absence of gravity. The exact location of the edge depends on how you define it. Some astronomers use galaxy counts, marking the edge as the distance where the density returns to the cosmic mean. Others use peculiar velocities, identifying the edge as the transition from outward flow to inward flow. Still others use gravitational lensing, tracing the edge by measuring the distortion of light from background galaxies. All three methods agree on the basic picture. The KBC Void extends roughly 500 million light-years in radius, with a transition zone spanning 100 to 200 million light-years. But the details differ, reflecting uncertainties in the measurements and differences in the definition of the boundary. The edge is also where the void's influence on cosmology becomes most apparent. Inside the void, the local expansion rate appears higher than the global average, creating the Hubble tension. At the edge, this effect begins to fade as the outward flow driven by surrounding structures weakens and the expansion rate returns to normal. The Milky Way sits near the center of the void, roughly 100 to 200 million light-years from the deepest point. This placement is unusual. Most galaxies live near the edges of voids, where the density is higher and interactions more frequent. The fact that the Milky Way is positioned near the center suggests either extraordinary luck or some unknown selection effect that biases observers towards central locations. The edge of the KBC Void is a frontier, a boundary between emptiness and structure, between isolation and connection. It is the place where the void meets the rest of the universe, where the underdensity that defines our cosmic address gives way to the walls and filaments that dominate the larger cosmic web. And somewhere between the center and the edge, the Milky Way floats, suspended in a gradient that stretches across 500 million light-years of space, watching the universe expand at a rate that should not be possible. The most direct impact is on the Hubble constant. This number governs the rate at which the universe expands, determining how fast galaxies recede and how old the cosmos is. Local measurements using supernovae and other distance indicators yield a value of roughly 73 kilometers per second per million light-years. But calculations based on the cosmic microwave background predict a value of 67 kilometers per second per million light-years. This 9% discrepancy is the Hubble tension, and it has persisted for years despite intense scrutiny. The KBC Void offers an explanation. Inside a region of a lower density, galaxies experience a gravitational pull from denser regions beyond the void's edge, inflating their velocities and making the universe appear to expand faster than it does on average. Calculations show that the void could inflate the local Hubble constant by 11%, just enough to reconcile the tension. But if the void is responsible for the Hubble tension, then every distance measurement made within 500 million light-years is biased. Supernovae appear dimmer than they should, their brightness reduced by the faster recession velocities inside the void. Galaxies appear more distant than they are, their redshifts inflated by the outward flow. cosmic distances, calibrated using local measurements, are systematically wrong. The void also affects measurements of dark energy. This mysterious force is inferred from observations of distant supernovae, whose brightness reveals how fast the universe expanded at different times in its history. But if local measurements are biased by the void, then the inferred properties of dark energy may be incorrect. The void creates an illusion of accelerated expansion locally, making dark energy appear stronger than it actually is. The cosmic microwave background is contaminated as well. This ancient light carries information about the universe when it was just 380,000 years old, but it also picks up signals from structures along the line of sight. As light crosses the KBC void, it loses energy in the integrated Sachs-Wolf effect, creating a cold spot in the microwave sky. This cold spot complicates interpretation, mixing primordial signals from the early universe with the imprint of the void. Baryon acoustic oscillations, ancient sound waves frozen into the distribution of galaxies, provide another measure of cosmic distances. These oscillations create a characteristic scale in galaxy clustering, a standard ruler that can be used to test cosmological models. Recent studies show that the KBC void affects baryon acoustic oscillation measurements, creating discrepancies between models that include the void and models that assume homogeneity. The statistics are striking. A 2025 analysis comparing void models to 20 years of baryon acoustic oscillation data found that a void model is roughly 100 million times more likely than a void-free model. This statistical confidence represents one of the strongest endorsements yet for the existence of the KBC void and its role in explaining the Hubble tension. The void also affects galaxy surveys. Astronomers use these surveys to map the large-scale structure of the universe, tracing the distribution of galaxies across billions of light-years. But if the local region is atypical, then surveys centered on the Milky Way are biased, overrepresenting voids and underrepresenting walls and filaments. Gravitational lensing studies are influenced as well. This technique uses the bending of light by mass to map the distribution of matter, both visible and dark. Inside the KBC void, the lensing signal is weaker because there is less mass to bend the light. This creates systematic errors in measurements of matter density and the clustering of galaxies. The motion of galaxies, measured through peculiar velocities, reveals the gravitational influence of surrounding structures. Recent observations show that bulk flows, the coherent motion of galaxies over vast distances, exceed predictions of the standard model by a factor of 4.8 standard deviations. Models that include the KBC void predict exactly these rapid bulk flows, offering independent confirmation that the void is real and influencing local dynamics. The void's impact extends to time-domain astronomy, the study of objects that change over time. Supernovae, variable stars, and other transient phenomena are used to calibrate distance scales and test cosmological models. But if distances are biased by the void, then the calibration is wrong, affecting estimates of the universe's age, the rate of structure formation, and the properties of dark energy. The void also influences measurements of the matter density. This parameter describes how much ordinary and dark matter the universe contains, governing the growth of structure and the fate of cosmic expansion. Inside a void, the matter density is lower than the cosmic average, creating a local bias that affects measurements made within 500 million light-years. Future missions will test these predictions. The Euclid Space Telescope, launched in 2023, is mapping the distribution of galaxies across billions of light-years with unprecedented precision. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field surveys of supernovae and galaxies, constraining the properties of dark energy and testing whether the void hypothesis is correct. Ground-based surveys continue as well. The Dark Energy Spectroscopic Instrument and the Vera Rubin Observatory are mapping millions of galaxies, tracing the cosmic web and measuring the growth of structure over cosmic time. These observations will reveal whether the KBC void is as large and deep as current estimates suggest, and whether it can explain the Hubble tension without invoking new physics. The void matters because it changes everything. It affects distances, expansion rates, the distribution of matter, and the properties of dark energy. It biases local measurements, distorts cosmological parameters, and challenges the assumption that our location is typical. If the void is real, then astronomy must account for it, correcting measurements for the local underdensity and recalibrating the cosmic distance ladder. But if the void is real, it also means that the standard model is incomplete, that gravity behaves differently on large scales, or that the universe is more structured than we believed. The void is not just a hole in space, it is a hole in our understanding, a gap between what we observe and what our equations predict. And filling that gap may require abandoning assumptions that have guided cosmology for nearly a century. The standard model of cosmology is in crisis. This is not hyperbole. This is the assessment of researchers who have spent decades refining the equations that describe the universe's evolution. The KBC Void alone falsifies the standard model at 6 standard deviations. Combined with the Hubble Tension, the model is ruled out at 7 standard deviations, dark matter crisis. 7 standard deviations is not a hint of trouble. In particle physics, 5 standard deviations is the threshold for claiming a discovery. 6 is proof. 7 is overwhelming evidence that something fundamental is wrong with the framework. The void should not exist, yet it does. The tension should not persist, yet it has for years. Cosmologists are responding by rewriting the models. Some are incorporating the void into simulations, testing whether the standard framework can accommodate such a large structure if initial conditions or parameters are adjusted. Others are abandoning the standard model entirely, exploring alternative theories of gravity that allow structures to grow faster and voids to become deeper than Einstein's equations predict. The most conservative approach is to accept the void as a rare but allowed fluctuation within the standard model. According to this view, the KBC void is simply an outlier, a low probability structure that formed through gravitational collapse despite being statistically unlikely. The fact that we live inside such a structure is explained by selection bias. Observers are more likely to emerge in unusual environments if those environments favour the formation of galaxies and stars. But this explanation struggles with the numbers. Simulations show that voids as large and deep as the KBC void appear in less than 3% of universes consistent with the standard model. The probability is so low that the void's existence alone contradicts the model at 6 standard deviations. Adding the Hubble tension pushes the combined disagreement to 7 standard deviations. A more radical approach is to modify gravity. Modified Newtonian dynamics, or MOND, alters the strength of gravitational attraction at very low accelerations, the regime that governs structure formation on cosmic scales. Under MOND, gravity becomes stronger on large scales, allowing matter to clump more efficiently and voids to grow deeper. Models based on MOND reproduce the KBC void naturally. The enhanced gravity predicted by MOND allows structures to form faster, creating deeper voids and denser filaments than the standard model allows. Simulations show that MOND cosmologies produce KBC-like voids as a common feature, not a rare outlier. These same models simultaneously explain the Hubble tension, predicting that local measurements of the expansion rate will exceed the global average by roughly 11%, matching observations. But MOND is controversial. It requires abandoning Einstein's general relativity on cosmic scales, replacing it with a modified theory that has not been fully developed or tested. Many astronomers remain skeptical, arguing that MOND introduces more problems than it solves, creating tensions with other observations such as the cosmic microwave background and gravitational lensing. Another approach is to revise dark energy. Some researchers propose that dark energy is not uniform, that it varies in strength across different regions of the universe. In this scenario, regions of lower matter density, like voids, experience stronger dark energy effects, accelerating their expansion faster than regions of higher density. This variable dark energy could explain why the KBC void is so large and so deep, creating a structure that exceeds the expected size limits. Yet another possibility is early dark energy, a new form of energy that affected the universe's expansion rate during its early stages. This hypothetical component could change the growth rate of structure, allowing larger voids to form and potentially resolving the Hubble tension. But early dark energy models are still speculative, requiring new physics that has not been observed or confirmed. Incorporating the void into cosmological simulations is challenging. The standard approach assumes homogeneity on large scales, treating the universe as smooth and uniform. But the KBC void violates this assumption, creating a local structure that must be accounted for in every calculation. Simulations that include the void must specify its size, depth, and shape, parameters that are still uncertain and subject to debate. Recent efforts have focused on Lemaitre-Tolman-Bondi models, solutions to Einstein's equations that describe spherically symmetric voids in an expanding universe. These models incorporate a cosmological constant, representing dark energy, and allow for radial variations in density. By fitting the void's profile to observations, researchers can test whether the standard model, augmented with a local underdensity, can explain the Hubble tension. Results are mixed. Some studies find that Lemaitre-Tolman-Bondi models can reproduce the observed Hubble tension if the void is large and deep enough. Others find inconsistencies, noting that the void distorts distance measurements in ways that conflict with observations of supernovae and baryon acoustic oscillations. A 2025 analysis comparing void models to 20 years of baryon acoustic oscillation data found that a void model is roughly 100 million times more likely than a void-free model. This statistical confidence represents one of the strongest endorsements yet for incorporating the void into cosmological models. But it also highlights the challenge. The standard model, as currently formulated, does not predict such structures. Rewriting the models means confronting uncomfortable questions. If the cosmological principle fails, if the universe is not homogeneous on large scales, then how do we interpret measurements made from our location? If gravity behaves differently than Einstein predicted, what other predictions of general relativity might be wrong? If dark energy varies across space, what determines its strength, and how does it evolve over time? The void forces cosmologists to reconsider assumptions that have guided the field for nearly a century. The assumption that our location is typical, the assumption that the universe looks the same from every vantage point, the assumption that gravity follows Einstein's equations on all scales. These assumptions made cosmology tractable, allowing researchers to build models that describe the universe's evolution from the Big Bang to the present day. But if the void is real, these assumptions may be wrong, and if they are wrong, then the models built on them must be revised, recalibrated, and perhaps replaced entirely. The void is not just a structure, it is a challenge, a test case for cosmology, a phenomenon that demands new physics or a new framework. The effort to rewrite the models is ongoing. Future observations will constrain the void's properties with greater precision, testing whether it is as large and deep as current estimates suggest. New simulations will explore alternative theories, comparing predictions against data and searching for frameworks that can accommodate both the void and the Hubble tension. But one thing is certain: the standard model, as it stands, cannot explain the KBC void. The void exists, the tension persists, and the models must change. What does it mean to exist in a region of cosmic scarcity? Not just to live on a planet or in a galaxy, but to inhabit a massive underdensity, a hole in the universe 2 billion light-years wide, where matter is 20 to 46% thinner than it should be. The KBC void is not just a structure, it is a context, a condition that shapes our view of reality and forces us to confront uncomfortable questions about our place in the cosmos. The first question is observational. Are we typical observers, experiencing a universe that looks roughly the same from every vantage point? Or are we atypical, living in a location that distorts measurements and biases conclusions? The cosmological principle assumes the former, stating that the universe is homogeneous and isotropic on large scales. But the KBC void violates this principle, creating a local environment that differs dramatically from the cosmic average. If we are atypical observers, then every measurement we make requires correction. Distance scales must account for the void's influence on redshifts. Expansion rates must be adjusted for the outward flow driven by surrounding structures. The properties of dark energy must be recalibrated to remove the bias introduced by our location. This is not a minor technical detail. This is a fundamental challenge to how astronomy is conducted. The second question is philosophical. Does living in a void make us special? The answer depends on what you mean by special. If by special you mean rare, then yes. Simulations show that voids as large and deep as the KBC void appear in less than 3% of universes consistent with the standard model. The probability is so low that the void's existence alone contradicts the model at 6 standard deviations. But rarity does not imply significance. The universe is vast, containing billions of galaxies spread across billions of light years. Even if only 3% of regions resemble the KBC Void, that still corresponds to countless locations where observers might emerge. The fact that we live in such a location may simply reflect selection bias. Observers are more likely to notice unusual features of their environment because those features affect what they see. The anthropic principle formalizes this idea. It states that any observations we make must be compatible with our existence as observers. If voids favor the development of intelligent life, by providing stable environments free from the disruptive influence of galactic collisions and radiation bursts, then we should not be surprised to find ourselves in a void. The void is not special. We are simply sampling the universe from a location where observers are more likely to exist. But this explanation is unsatisfying. It replaces one mystery with another, trading the question of why we live in a void for the question of why voids favor observers, and it offers no testable predictions, no way to confirm or refute the hypothesis. The anthropic principle explains everything and nothing, a philosophical escape hatch that avoids the harder question: is the void real, or is it an artifact of incomplete data? The evidence increasingly favors reality. Galaxy surveys show a consistent deficit in the galaxy count within 500 million light-years of the Milky Way. Baryon acoustic oscillation data presented at the National Astronomy Meeting in 2025 showed that a void model is roughly 100 million times more likely than a void-free model. The bulk flow of galaxies, measured through peculiar velocities, matches the predictions of models that include the void. The Hubble tension, a 9% discrepancy in the local expansion rate, aligns with the 11% inflation predicted by the void's outward flow. The void also raises questions about the nature of structure. Why do voids dominate 90% of the universe's volume? Why is matter concentrated along thin filaments and walls, leaving vast interiors nearly empty? The standard model attributes this to gravitational collapse, the relentless pull of matter toward overdense regions and away from underdense ones. But the KBC void is too large, too deep, and too extreme to be explained by this process alone. Modified gravity offers an alternative. Under theories like MOND, gravitational attraction becomes stronger at very low accelerations, the regime that governs structure formation on cosmic scales. This enhanced gravity allows matter to clump more efficiently, creating deeper voids and denser filaments than Einstein's equations predict. Simulations based on MOND reproduce KBC-like voids as a natural consequence, not a rare outlier. But accepting modified gravity means abandoning general relativity on large scales, overturning a century of physics that has passed every experimental test. It means rewriting textbooks, recalculating predictions, and confronting the possibility that our understanding of gravity is incomplete. The philosophical weight of this decision is enormous, far exceeding the technical challenge of revising equations. The void also forces us to confront the limits of observation. We cannot step outside the void and measure the universe from a neutral location. We are embedded in the structure we are trying to study, our measurements filtered through the lens of our environment. This is not unique to cosmology. All observations are made from a specific vantage point, but the void makes the bias explicit and unavoidable. The Milky Way sits near the center of the KBC Void, roughly 100 to 200 million light-years from the deepest point. This placement is unusual. Most galaxies live near the edges of voids, where the density is higher and interactions more frequent. The fact that the Milky Way is positioned near the center suggests either extraordinary luck or some unknown selection effect that biases observers towards central locations. The philosophical weight of the void is not just about cosmology. It is about how we understand our place in the universe. Are we typical or atypical, central or marginal, living in abundance or scarcity? The void suggests scarcity, a cosmic address defined by absence rather than presence, by emptiness rather than structure. We are not floating in a sea of galaxies. We are suspended in a bubble, surrounded by a gulf so vast it distorts our measurements and challenges our assumptions. But scarcity is not insignificance. The void is the dominant feature of the cosmos, occupying 90% of the volume and defining the architecture of existence. To live in a void is not to live on the margins, but to inhabit the baseline, the empty canvas on which the universe paints its structures. We are not isolated. We we are embedded in the very fabric that holds the cosmos together. The void is a mirror. It reflects back our assumptions, our biases, and our limitations. It forces us to ask whether what we see is real or artifact, whether our models describe the universe or merely our corner of it, and it demands that we confront the possibility that the cosmos is stranger, more structured, and more variable than we dared imagine. The KBC Void is not a cosmic accident. It is part of a pattern, a family of structures that repeat across the universe at different scales and depths. If one supervoid exists, then others must as well, scattered across billions of light years like bubbles in foam. The search for these structures has become a priority, a systematic effort to map the universe's emptiness and determine whether voids like the KBC are rare outliers or common features. Galaxy surveys are the primary tool. Over the past 2 decades, astronomers have catalogued millions of galaxies across vast regions of sky, measuring their positions and redshifts to build 3-dimensional maps of the cosmos. These surveys reveal the cosmic web in exquisite detail, tracing filaments, walls, and voids across billions of light years. The Sloan Digital Sky Survey was among the first to systematically identify voids. Beginning in the early 2000s, this project mapped the distribution of galaxies across a quarter of the sky, revealing thousands of voids ranging from tens of millions to hundreds of millions of light years across. The data showed that voids are not rare anomalies but common features, occupying 90% of the universe's volume. But most of these voids are typical, spanning a few hundred million light years and containing roughly 1/10 the cosmic average density. The KBC Void is different. It is 7 times larger than a typical void, reaching nearly 1 billion light years in diameter and 20 to 46% below the cosmic mean in density. Structures this extreme are predicted to be rare, appearing in less than 3% of universes consistent with the standard model. The search for other supervoids has yielded mixed results. The Boötes void, discovered in 1981, remains one of the largest and emptiest regions ever measured. It stretches 330 million light-years across and contains only 60 galaxies, far fewer than expected for a region of that size. But the Boötes void is smaller than the KBC void, and its density contrast, while extreme, does not reach the 46% deficit observed within 500 million light-years of the Milky Way. The Eridanus supervoid, associated with the cold spot in the cosmic microwave background, may approach the KBC void in size. This massive underdensity lies in the southern sky, potentially stretching up to 1 billion light-years across. As ancient light from the Big Bang crosses the Eridanus supervoid, it loses energy in the integrated Sachs-Wolf effect, creating the observed cold spot. But the exact size and depth of the Eridanus supervoid remain uncertain, with estimates varying depending on the methods used to measure it. Other large voids have been catalogued by more recent surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping the distribution of galaxies across billions of light-years with unprecedented precision. Early results hint at deviations from the standard model, observations that suggest the presence of large-scale structures not predicted by the equations. Baryon acoustic oscillation data presented at the National Astronomy Meeting in 2025 showed that a void model is roughly 100 million times more likely than a void-free model when tested against 20 years of observations. This statistical confidence represents one of the strongest endorsements yet for the existence of large local voids and their role in explaining anomalies like the Hubble Tension. But the search extends beyond the local universe. Astronomers are mapping voids at greater distances, tracking how their properties have evolved over cosmic time. Ancient voids, observed as they were billions of years ago, provide a window into the universe's early structure formation. Comparing these ancient voids to nearby voids reveals how dark energy has influenced the growth of structure, whether voids have expanded faster or slower than predictions, and whether the properties of dark energy have changed over time. The Euclid Space Telescope, launched in 2023, is conducting wide-field surveys designed specifically to study the large-scale structure of the universe. Euclid's infrared cameras can detect faint galaxies across billions of light-years, tracing the distribution of matter and mapping voids with unprecedented detail. Early observations are expected to reveal whether supervoids like the KBC are truly rare or simply overlooked in previous surveys. ground-based surveys continue as well. The Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, will conduct the legacy survey of space and time, mapping the entire southern sky every few nights for a decade. This survey will catalogue billions of galaxies, providing the most comprehensive map of the cosmic web ever produced. The data will reveal the distribution of voids across the observable universe, testing whether structures like the KBC Void are common features or statistical outliers. The search for other voids is not just about counting structures. It is about testing the standard model of cosmology, determining whether the universe is as homogeneous as we believed, and understanding whether our location inside the KBC Void is typical or atypical. If supervoids are common, then the standard model may need revision, incorporating enhanced structure formation or modified gravity to explain why such large structures form. If supervoids are rare, then the KBC Void represents an extraordinary cosmic address, a location so unusual it challenges the assumptions that guide cosmology. The anthropic principle suggests that observers are more likely to emerge in unusual locations if those locations favour the development of intelligent life. But this explanation is controversial, replacing one mystery with another. Recent studies have also searched for voids using peculiar velocities, the motion of galaxies relative to the smooth expansion of the universe. Voids create systematic flows, pulling galaxies outward toward denser regions beyond their boundaries. By measuring these flows, astronomers can identify voids even when galaxy counts are incomplete or biased. The bulk flow curve, a measure of the collective motion of galaxies over vast distances, provides independent evidence for the KBC Void. Recent observations show that galaxies within 250 million light-years of the Milky Way move outward faster than the standard model predicts, their velocities matching the pattern expected for a massive underdensity. This agreement between theory and observation strengthens the case that the void is real and influencing local dynamics. The search for other voids is ongoing. Future surveys will map the universe with greater precision, revealing the distribution of emptiness across billions of light-years and testing whether supervoids are common or rare. These observations will determine whether the KBC Void is an isolated anomaly, a statistical outlier that challenges the standard model, or part of a larger pattern that reveals new physics on cosmic scales. And as we map more of the universe, as we catalogue more voids and measure their properties with greater accuracy, we may discover that the wholes outnumber the substance, that emptiness is not absence, but the foundation upon which all structure rests. The KBC Void raises more questions than it answers. After decades of observation, thousands of research papers and countless simulations, fundamental mysteries remain. How did the void form? Why is it so large? What does it mean for the future of the universe? And most troubling of all, can we trust anything we measure from inside it? The first unanswered question is origin. Voids form through gravitational collapse, matter flowing away from underdense regions toward overdense ones. But the KBC Void is 7 times larger than a typical void, deeper in its underdensity, and positioned in a way that challenges the standard model. The standard model predicts that voids this extreme should appear in less than 3% of universes, yet here it is, surrounding us, impossible to ignore. Modified gravity offers one explanation. Under theories like MOND, gravitational attraction becomes stronger at very low accelerations, allowing structures to grow faster and voids to become deeper than Einstein's equations predict. Simulations based on MOND reproduce KBC-like voids naturally, treating them as common features rather than rare outliers. But MOND remains controversial, requiring abandonment of general relativity on cosmic scales. Another possibility is that the void formed from unusual initial conditions in the early universe. Perhaps the density fluctuations imprinted during inflation were stronger, or more organized than the standard model assumes, creating seeds for larger structures. But this explanation struggles with observations of the cosmic microwave background, which shows remarkably uniform temperature fluctuations. The second question is influence. How much does the void affect our measurements? The local Hubble constant exceeds global predictions by 9%. Calculations show that the void could inflate the local expansion rate by 11%, just enough to reconcile the tension. But this solution requires that the Milky Way sit near the void's center, a placement that appears unusual. Baryon acoustic oscillation data presented in 2025 provided the strongest evidence yet. Analysis of 20 years of observations showed that a void model is roughly 100 million times more likely than a void-free model. This statistical confidence represents a major endorsement for the void hypothesis, yet uncertainties remain about the void's exact size, depth, and shape. The third question is representativeness. Are our measurements typical of the universe, or are they biased by our location inside the void? If the void inflates the local Hubble constant by 11%, then distance measurements within 500 million light-years are systematically wrong. Supernovae appear dimmer, galaxies appear more distant, and the universe appears older or younger than it actually is. This bias extends to dark energy. The mysterious force accelerating cosmic expansion is inferred from observations of distant supernovae. But if local measurements are contaminated by the void, then the inferred properties of dark energy may be incorrect. The void creates an illusion of accelerated expansion locally, making dark energy appear stronger than it actually is. The fourth question is uniqueness. Is the KBC Void a rare anomaly, or are supervoids common features of the universe? Surveys have catalogued thousands of voids, but most are typical, spanning a few hundred million light-years and containing roughly 1/10 the cosmic average density. Structures as extreme as the KBC Void remain rare. Future missions will test this. The Euclid Space Telescope and the Vera Rubin Observatory are mapping the universe with unprecedented precision, revealing the distribution of voids across billions of light-years. These observations will determine whether supervoids are common or outliers, and whether the KBC Void is part of a larger pattern. The fifth question is fate. What will happen to the void as the universe continues to expand? Dark energy drives cosmic acceleration, pushing space apart faster now than at any time in the past. Inside voids, where matter is scarce and gravity weak, dark energy's influence is stronger, driving expansion faster than in denser regions. Over tens of billions of years, the void will grow emptier, galaxies will drift outward, their separations increasing until neighbouring galaxies disappear beyond the cosmic horizon. The Milky Way, positioned near the void's centre, will become increasingly isolated, watching as the cosmic web dissolves and darkness claims the sky. The sixth question is implications. If the void is real, what does it mean for cosmology? The standard model assumes homogeneity on large scales, treating the universe as smooth and uniform. But the KBC Void violates this assumption, creating a local structure that must be accounted for in every calculation. Rewriting the models means confronting uncomfortable questions. If the cosmological principle fails, how do we interpret measurements made from our location? If gravity behaves differently than Einstein predicted, what other predictions might be wrong? If dark energy varies across space, what determines its strength and how does it evolve? The seventh question is resolution. How will the Hubble tension be settled? Will the void explain it, or will new physics be required? Dr. Indranil Banik, a leading researcher on the void, has calculated that its influence could account for an 11% increase in the locally measured Hubble constant, just enough to reconcile the discrepancy. His neutrino hot dark matter model, based on MOND, predicts both the void and the tension as natural consequences. But alternative explanations remain. Early dark energy, a hypothetical component that affected the universe's expansion shortly after the Big Bang, could also resolve the tension. This model introduces new physics without invoking modified gravity, but it faces challenges reconciling with other observations. The eighth and final question is truth. Is the void real, or is it an artifact of incomplete data, selection effects, or observational bias? The evidence increasingly favours reality, but doubt remains. Future observations will test the void hypothesis with greater precision, constraining its size, depth, and influence on local measurements. The unanswered questions are not weaknesses. They are the engine of discovery, the gaps in understanding that drive science forward. The KBC Void is a challenge, a test case for cosmology, a phenomenon that demands new physics or a new framework. And until these questions are answered, the void will remain what it has always been, a hole in space, a mystery carved into the fabric of reality, and a reminder that the universe still holds secrets we're only beginning to glimpse. You are made of atoms forged in the hearts of dying stars. Your bones contain calcium from supernovae that exploded billions of years ago. Your blood carries iron scattered across space by cosmic violence. Every breath you take is borrowed from the universe, atoms cycling through stars and planets and living things across 14 billion years of cosmic history. And all of this, every atom, every moment, every thought, unfolds inside a hole 2 billion light-years wide. The KBC Void is not a prison. It is a context, a stage on which existence plays out. The Void does not diminish us. It frames us, revealing our place in a cosmos dominated by emptiness yet rich with structure. We are not isolated. We are embedded in the very fabric that defines the universe's architecture. The evidence is now overwhelming. Galaxy surveys show a consistent deficit in the galaxy count within 500 million light-years of the Milky Way. Baryon acoustic oscillation data presented at the National Astronomy Meeting in 2025 showed that a void model is roughly 100 million times more likely than a void-free model. The bulk flow of galaxies matches predictions of models that include the void. The Hubble tension aligns with the 11% inflation predicted by the void's outward flow. The void is real, the tension is real, and the universe does not look the same from every location. But this is not a tragedy. It is a revelation. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, was always an approximation, a simplification that made the mathematics tractable. The void shows us that the approximation breaks down, that the universe is more structured, more organized, and more variable than the principle allows. We live in a region of cosmic scarcity, where matter is 20 to 46% below the cosmic mean. But scarcity is not absence. The void contains galaxies, clusters, dark matter, and all the raw material for structure formation. It is emptier than average, yes, but it is not empty. It is a canvas on which the universe paints its structures, a stage where gravity, dark energy, and cosmic expansion perform their eternal dance. The Milky Way sits near the center of this void, roughly 100 to 200 million light-years from the deepest point. This placement is unusual, perhaps even improbable, but it is also our home, the cosmic address where life emerged, where intelligence evolved, and where we first looked up and asked, what are we, and where do we fit in the grand design? The void does not answer this question, it reframes it. We are not observers at the center of the universe, not privileged witnesses standing outside the cosmic machinery. We are participants, embedded in a structure that shapes what we see and how we interpret it. Our measurements are biased by our location, our models are incomplete, and our understanding is constrained by the lens through which we view reality. But this is not a limitation. It is a challenge, an invitation to build better models, to refine our measurements, and to confront the uncomfortable truth that the universe is stranger than we imagined. The void forces us to abandon assumptions that have guided cosmology for nearly a century, to question whether gravity behaves as Einstein predicted, and to consider whether dark energy varies across space. The future will bring answers. The Euclid Space Telescope and the Vera Rubin Observatory are mapping the universe with unprecedented precision, revealing the distribution of voids across billions of light-years. These observations will test whether the KBC Void is as large and deep as current estimates suggest, whether supervoids are common or rare, and whether the void hypothesis can explain the Hubble tension without invoking new physics. But even if the void is confirmed, even if every prediction is verified and every measurement aligns, the deeper questions will remain. Why does the universe organize itself into voids and filaments? Why is 90% of space empty? Why did a life emerge in a region of cosmic scarcity rather than abundance? The void offers no answers. It offers only a perspective, a way of seeing the cosmos that acknowledges emptiness as the baseline, structure as the exception, and ourselves as inhabitants of the in-between. We are not floating in a sea of galaxies. We are suspended in a bubble, surrounded by a gulf so vast it distorts our measurements and challenges our assumptions. But the bubble is not a barrier. It is a boundary, a transition zone where emptiness gives way to structure, where isolation meets connection, and where the universe reveals its true architecture. Beyond the void's edge lie walls and filaments, massive concentrations of galaxies that define the cosmic web. The Shapley concentration pulls galaxies outward with the force of 10,000 trillion suns. The Laniakea supercluster spans 500 million light-years, a river of galaxies flowing toward distant attractors. We are not alone. We are connected to this larger structure, our motion shaped by gravity across hundreds of millions of light-years, our evolution influenced by forces we are only beginning to understand. The void does not isolate us. It positions us, giving us a vantage point from which to observe the universe's grand design. The KBC Void is a home in the emptiness. It is where we live, where we evolved, and where we first looked up and wondered about our place in the cosmos. It is not the centre of the universe. It is not a special location. It is simply one bubble among countless others, one region of cosmic scarcity in a universe dominated by absence. But it is ours, and that makes it extraordinary. You are floating through a hole in space 2 billion light-years wide, watching the universe expand at a rate that should not be possible, suspended in emptiness that defines the very fabric of reality. This is not a flaw. This is not a mistake. This is the cosmos revealing itself, showing you that absence is not nothing, that emptiness is not void, and that the spaces between the light hold secrets we are only beginning to glimpse. The void is real. The void is home, and the journey has only just begun.